At the very beginning of time, there was nothing. No matter, no energy, just absolute emptiness. And then, in a flash so brief it defies comprehension, that nothing transformed into everything. Space exploded into existence. Time began to move. Tiny particles raced outward, forming the seeds of galaxies, planets, and life itself. How could something as vast and complex as the universe come from a state of total absence? How did the deepest silence erupt into a cosmic roar? How did nothing light the spark that became the Big Bang? Before we begin tonight's video, let us know where in the world you're watching from and what time it is for you right now. Post it in the comments below and settle in for a fascinating journey to the beginning of the universe. The idea of nothing may sound simple, but in reality it's one of the most puzzling and mind-bending topics in all of human thought. For thousands of years, from the time of ancient philosophers to the age of modern science, people have been trying to understand what nothing really means. And as strange as it may sound, the word nothing doesn't have just one clear meaning. Its definition changes depending on who's using it, whether it's a philosopher, a scientist, or even a physicist working on theories about the birth of the universe. Especially when we start asking what existed before the Big Bang, or how everything could have come from nothing, we first need to understand exactly what that word means. In philosophy, nothing is usually taken to mean absolute non-existence, the complete absence of anything at all. No matter, no energy, no space, no time, not even empty air or invisible forces, just nothing. This is not an easy idea to grasp because we have no experience of such a thing. Even what we call empty in everyday life, like the air in a room or the space between stars, is still filled with gases, particles, light, or invisible fields. Take the ancient Greek philosopher Aristotle, for example. He lived over 2,300 years ago and argued that a truly empty space could not exist. He believed that nature hated a vacuum and that all space must be filled with something, even if that something was invisible, like a kind of subtle fluid or mysterious ether. His ideas were partly a response to earlier thinkers, known as atomists, who believed the universe was made of tiny indivisible particles moving around in an infinite void. But Aristotle thought that nothingness wasn't real emptiness. It was just when something lacked a specific quality or form, not when it had no existence at all. In ancient times, the idea that something could come out of true nothingness was very hard to accept. Instead, most believed that creation meant reshaping materials that had always been there, or that everything flowed out from a divine or eternal source. Then, in the early 18th century, the German philosopher Gottfried Wilhelm Leibniz asked a powerful question: why is there something rather than nothing? This simple but deep question lies at the heart of all philosophical inquiry into existence. If nothingness is the most basic, natural state, then why does anything exist at all? Why are we in a universe filled with stars, planets, energy, and time? Some thinkers believe this question can't be answered by science alone. It's also about purpose and meaning. In fact, certain philosophical views like existentialism see nothing, not as physical emptiness, but as the lack of built-in meaning in the universe. If the universe has no predetermined purpose, then it's up to humans to create meaning for themselves. But when we move from philosophy into science, the idea of nothing takes on a very different shape. For a long time, scientists also believed that empty space was simply a background, an empty stage where the events of the universe played out. That view started to change in the 17th century. Around the year 1643, Italian scientist Evangelista Torricelli made a discovery that helped prove the existence of a vacuum. He showed that when mercury is poured into a sealed glass tube and turned upside down, it leaves a space above the mercury with no air. A real vacuum. This simple device, called a barometer, led to further experiments by people like Blaise Pascal and Robert Boyle. Their work challenged Aristotle's belief that all space had to be filled and helped scientists see that empty space was real and could be studied. Even so, many still found the idea of a truly empty void uncomfortable. In the 19th century, physicists came up with the idea of the luminiferous ether, a mysterious invisible substance they believed filled all of space and allowed light waves to travel through it. But this theory fell apart in the early 20th century, when Albert Einstein's theory of relativity showed that light didn't need a medium like the ether to move through space. Then came one of the biggest scientific revolutions of all, quantum mechanics. In the early 20th century, scientists discovered that what we once thought of as empty space wasn't empty at all. Even when you remove all particles from a region of space, that space still isn't truly nothing. Thanks to the Heisenberg uncertainty principle, we now know that certain properties, like energy and time, can never both be perfectly known at the same time. This means that even in what looks like total emptiness, there's still a flicker of activity. Space is filled with tiny temporary particles that constantly appear and disappear in a flash. These virtual particles may be invisible, but they leave behind effects that scientists can measure. One of the best examples of this is called the Casimir effect. In the year 1948, Dutch physicist Hendrik Casimir predicted something strange. If you place two uncharged metal plates very close together in a vacuum, they will slowly move toward each other, even though nothing seems to be pulling them. This happens because fewer virtual particles can exist in the small gap between the plates than in the space outside them. That creates an imbalance in pressure, which gently pushes the plates together. Later experiments confirm that Casimir was right. The force between the plates proves that the quantum vacuum, the so-called empty space, is alive with energy. Scientists call this invisible energy zero-point energy, and it's the lowest possible energy level that a quantum field can have, even when the temperature is absolute zero. In today's science, especially in quantum field theory, every fundamental particle is seen not as a tiny ball, but as a ripple in a larger field that fills all of space. There's an electron field, a photon field, a quark field, and many others. What we call empty space is really just these fields in their calmest state, without any ripples or excitations. But even in this quiet state, the fields are still there, humming faintly with energy. One of the most famous fields is the Higgs field, which gives particles their mass. Even when the Higgs field is at rest, it still has a non-zero value, meaning that mass can exist only because the vacuum isn't truly empty. So in science, nothing is not the same as in philosophy. The scientific version of nothing is actually something. It's a restless sea of invisible fields and energy. Now let's return to the biggest question of all. What came before the Big Bang? The standard model of cosmology says that the universe began from an incredibly hot and dense point known as a singularity. At that moment, all matter, all energy, even space and time itself came into existence. This means there was no before in the usual sense because time didn't exist yet. If time started at the Big Bang, then asking what happened before is like asking what's north of the North Pole. It simply doesn't apply in the usual way. Still, scientists have come up with ideas to go even deeper. Some modern theories suggest that the Big Bang wasn't truly the beginning. Maybe it was a kind of transition, a bounce from an earlier universe or a phase shift from another state of reality. In cyclic models, for instance, the universe goes through endless cycles of expansion and collapse. In this view, what we call nothing before our universe might have been the compressed remains of a previous one, or a pause between two cosmic phases. So even if the current universe had a beginning, it might not have been the first universe to ever exist. One of the most powerful and fascinating ideas about the beginning of the universe comes from a theory known as inflationary cosmology. According to this idea, the universe didn't start out expanding slowly. It began with a burst of unbelievably fast expansion that happened during the earliest moments of time, just a tiny fraction of a second after the universe came into existence. This explosive growth was driven by something scientists call the inflaton field, a kind of mysterious energy field that caused space itself to stretch faster than the speed of light. In some versions of this theory, the Big Bang might not have been the true beginning at all. Instead, it could have been the result of a strange and tiny quantum fluctuation, a kind of random energy ripple, in what scientists call a quantum vacuum or a false vacuum. This was not ordinary empty space, but rather a strange high-energy state filled with potential. At some point, this vacuum suddenly decayed, releasing a tremendous amount of energy. That burst of energy then created all the matter and light we see in the universe today. So, in this view, the term nothing doesn't mean a complete absence of everything. It means something very different, an unstable and energetic quantum vacuum, a kind of invisible soup bubbling with potential. This nothing might even be part of something far bigger, something scientists call a metavacuum, which could give birth to many universes instead of just one. This idea is part of what's known as the multiverse hypothesis. In such a grander picture, our universe could be just one bubble floating in a vast cosmic sea, constantly spawning new universes through bursts of energy. Instead of thinking of nothing as an empty void, some scientists describe it as a kind of quantum foam, a bubbling, restless foundation of reality filled with tiny fluctuations. This foam might be the true stage from which the universe emerged, not a lifeless emptiness, but a creative and fertile background for new worlds to form. To truly understand this mysterious nothing, scientists are working on a much deeper question. How do we unify the two most important theories in physics? On one side, we have Einstein's general relativity, which explains gravity and the behavior of stars, galaxies, and black holes. On the other side, we have quantum mechanics, which describes atoms, particles, and the tiniest building blocks of matter. Merging these two into a single theory is the goal of quantum gravity, a theory that could finally explain what really happened before the Big Bang. One promising idea in this direction is loop quantum gravity. This theory suggests that space and time are not smooth like a sheet of fabric. Instead, they are made of incredibly tiny, indivisible units, like loops or building blocks. According to this model, the universe didn't collapse into a point of infinite density at the Big Bang. Instead, it shrunk to a smallest possible size and then bounced back, beginning its expansion. This event is called a quantum bounce. If this idea is right, then there was never a true singularity, and there was no complete nothing before the Big Bang, just a strange state before expansion. Another fascinating approach comes from string theory, a theory that tries to describe everything in the universe using tiny, vibrating strings instead of point-like particles. String theory also suggests that there are extra dimensions of space, not just the 3 we see, but possibly 9 or more, curled up so small that we don't notice them. In some string theory ideas, our universe could have started when 2 giant higher dimensional surfaces called branes collided. These branes float in a larger invisible space known as the bulk. Before our universe began, there could have been a whole other reality in this bulk, a place filled with energy, movement, and possibility. In this view, nothing before the Big Bang may have actually been this other dimensional brane world, or even the bulk space itself. It's not a cold, empty void. It's a wild and dynamic realm that might not include space and time as we know them, but which has the power to give rise to them. What all these theories show is that the scientific concept of nothing is far more complicated than it first seems. Instead of a pure, total emptiness, it looks more like a strange, energetic, and ever-changing environment, something with rules, patterns, and the seeds of creation hidden within it. Whether it is a quantum vacuum bubbling with virtual particles, a shrunken universe ready to bounce back, a cosmic brain preparing to collide, or a network of tiny strings and loops, the idea of nothing in modern science is always something with structure, behavior, and potential. This is where science and philosophy begin to part ways. In philosophy, nothing often means the complete absence of anything at all. No space, no time, no laws, not even potential. But in science, when researchers talk about nothing, they usually mean something else entirely, a scientific vacuum, or a state where energy is low but quantum fields still exist. In such a vacuum, space and time may not have taken shape yet, but there's still something going on at a deeper level. The big question, can something come from true, absolute nothingness, remains unanswered by science. That's a question for philosophy, because science can only study things that can be measured, tested, and observed. And true nothingness, if it even exists, is something we might never be able to study. Still, the search to understand this mysterious nothing continues to inspire scientists, philosophers, and dreamers alike. As we dig deeper into the secrets of the universe, we find that what we once thought was empty is actually full of mystery, activity, and possibility. Understanding what, if anything, came before the Big Bang may depend entirely on how we choose to define that ever-elusive concept. Nothing. The Big Bang Theory is currently the most widely accepted explanation for how our universe began and how it has changed over time. The Big Bang Theory is currently the most widely accepted explanation for how our universe began and how it has changed over time. It tells the story of how the universe started out in an unimaginably hot, dense state, so small it could barely be called space, and then began expanding. Over billions of years, this expansion cooled the universe, allowing it to form the stars, galaxies, and complex structures we observe today. But it's important to clear up a common misunderstanding. The Big Bang was not an explosion in space. It wasn't like a firecracker going off in the middle of a dark, empty room. Instead, it was the expansion of space itself. Every point in the universe stretched away from every other point. Matter and energy didn't move through space. They were carried along as space itself grew larger. This idea is central to the Big Bang theory and helps us understand that the universe has a history. It has been changing dramatically since it began. The development of this theory didn't happen overnight. It was built step by step, over many decades, based on careful observations and bold ideas. One of the earliest and most influential thinkers was Georges Lemaitre, a Belgian priest and physicist who, in the 1920s, suggested that the universe had started from what he called a primeval atom, a single, extremely dense point of matter and energy that expanded outward. This idea laid the foundation for what would become the Big Bang theory. Strangely, the name Big Bang wasn't meant to be taken seriously at first. It was actually coined in a dismissive tone by Fred Hoyle, an English astronomer who believed in a completely different idea known as the steady-state theory. He used the term to mock Lemaitre's idea of a beginning to the universe, but the name stuck and, ironically, became the official term for the theory he opposed. A major leap forward came in the late 1920s when American astronomer Edwin Hubble made a surprising discovery. He found that distant galaxies were moving away from Earth, and the farther away a galaxy was, the faster it seemed to be moving. This became known as Hubble's law. The light from these galaxies was stretched toward the red end of the spectrum, a phenomenon called redshift, similar to how a siren sounds lower as an ambulance drives away. This redshift showed that space itself was expanding, pulling galaxies apart. Hubble's work offered the first direct observational evidence that the universe was growing, just as Lemaitre had predicted. During the middle of the 20th century, there was a heated debate between two major ideas, the Big Bang theory and the steady-state theory. The steady-state model claimed that the universe had no beginning or end. It said that although the universe was expanding, new matter was constantly being created to fill in the gaps, so it always looked the same overall. For a while, both theories had their supporters, but then two monumental discoveries changed everything. In the year 1964, scientists Arno Penzias and Robert Wilson were using a large horn-shaped antenna when they picked up a strange, persistent hiss, like static from all directions in the sky. At first, they thought it was just noise from the equipment, or even pigeon droppings in the antenna. But it turned out to be something far more important, the cosmic microwave background, or cosmic microwave background. This faint glow is the leftover radiation from the very early universe. According to the Big Bang theory, the universe once looked like a hot, dense fog of particles and radiation. As it expanded and cooled, it eventually became clear enough for light to travel freely. That ancient light is what we now detect as the cosmic microwave background. It is like a frozen snapshot of the universe when it was just 380,000 years old, a baby in cosmic terms. Its smooth temperature pattern across the sky matches exactly what the Big Bang theory predicts. This discovery became one of the strongest pieces of evidence for the theory. The second major discovery came from studying the amounts of light elements in the universe, things like hydrogen, helium, and small traces of lithium. The Big Bang theory predicts that during the universe's first few minutes, it was hot enough for nuclear fusion, the same process that powers the sun, to occur. In this short time, particles fused together to create the nuclei of these light elements in a process called Big Bang nucleosynthesis. And here's the amazing part. When scientists measured the actual amounts of these elements in the universe, they matched the predictions of the Big Bang model almost perfectly. About 75% of the visible matter in the universe is hydrogen, and about 25% is helium, just as expected. This exact match was a huge confirmation that the Big Bang really happened. Together, these three pillars, the expanding universe, the cosmic microwave background, and the abundance of light elements, form a solid foundation for the Big Bang theory. The true beginning of the universe is still wrapped in mystery. Scientists believe everything began at a moment known as the Planck epoch, which was just 1/10 million trillionth of a second after time itself started, about 10 to the power of minus 43 seconds. During this tiny sliver of time, the universe was so hot and dense that the four fundamental forces, gravity, electromagnetism, the strong nuclear force, and the weak nuclear force, were all combined into a single force. But our current physics breaks down here. We simply don't have a complete theory to describe what exactly happened at that moment. Right after the Planck epoch, something astonishing is thought to have happened. A burst of incredibly fast expansion known as inflation. This idea was proposed in the early 1980s, mainly by physicist Alan Guth, to solve several problems in the original Big Bang model. One problem was the horizon problem. How could parts of the universe so far apart have the exact same temperature if light hadn't had time to travel between them? Another was the flatness problem. Why does space seem almost perfectly flat rather than curved in some way? And finally, the monopole problem. If certain strange, heavy particles should have been created in the early universe, why haven't we found any? Inflation suggests that the universe expanded by a factor of at least 10 to the power of 26 in a fraction of a second. That's a number so large, it's hard to even imagine. This rapid expansion would have smoothed out the universe, flattened its geometry, and diluted any unwanted particles. It also explains the tiny ripples in the early universe, small fluctuations in density that later grew into galaxies and clusters of galaxies. After inflation ended, the universe didn't stop growing, but it slowed down. The energy from inflation was transformed into a hot, dense mixture of particles and forces called a quark-gluon plasma. It was so hot that even the building blocks of protons and neutrons, tiny particles called quarks, couldn't stick together yet. But as the universe expanded, it cooled. Eventually, the strong nuclear force became strong enough to bind quarks into protons and neutrons. This era is known as the Hadron epoch. During this time, there was a tiny imbalance. For every billion particles of antimatter, there were 1,000,001,000 particles of matter. As the universe cooled further, matter and antimatter collided and destroyed each other. But that little extra bit of matter survived. And that's what makes up everything we see today, from stars and planets to you and me. A few minutes after the Big Bang, when the universe had cooled to about 1 billion degrees Celsius, conditions were just right for nuclear fusion. Protons and neutrons fused together to form the nuclei of the first elements: deuterium, a form of hydrogen, helium-3, helium-4, and tiny amounts of lithium-7. These reactions lasted for only about 20 minutes, but their results are still all around us. The exact mix of these elements is one of the strongest and clearest signs that the universe really began in a hot, dense state, just as the Big Bang theory says. For the next few 100,000 years after the Big Bang, the universe was in a hot, thick, and glowing state. It wasn't yet the clear space we know today. Instead, it was filled with a dense soup of ionized hydrogen and helium nuclei, which means the atoms were broken apart into their cores and free-floating electrons. Light particles, called photons, were everywhere, but they couldn't travel far. Every time they tried to move, they bounced off those free electrons, getting absorbed or scattered. The result was a universe that looked like a glowing fog, completely opaque, meaning light couldn't pass through it. This time in the universe's life is known as the photon epoch. During this period, light, or radiation, was the most important and powerful form of energy. It ruled over matter, shaping the behavior of the cosmos. But the universe didn't stay in that hot, foggy state forever. As space expanded, it also cooled down. Around 380,000 years after the Big Bang, the temperature finally dropped to about 3,000 Kelvin, which was just cool enough for something amazing to happen. The free electrons began to join together with hydrogen and helium nuclei, forming the very first stable atoms. This moment is called recombination, and it changed everything. Once atoms were formed, light was no longer constantly bumping into loose charged particles. Now, photons could finally travel freely across the universe without being stopped. Space became transparent for the first time. The light from that moment is still around us today. It's incredibly faint and stretched into the microwave part of the spectrum, but we can still detect it. It's called the cosmic microwave background. Cosmic microwave background. The oldest light we can see, a kind of glowing baby picture of the universe. Scientists often call it the surface of last scattering, because it marks the last time photons scattered before streaming freely into space. It gives us a direct view of what the early universe looked like just after it became transparent. But after this glowing moment, a deep silence followed. The universe entered a long, dark period called the Cosmic Dark Ages. For hundreds of millions of years, there were no stars, no galaxies, no new light. Space was filled with nothing but cold, neutral hydrogen and helium gas, and the faint background glow of the cosmic microwave background. It was a time of stillness, with only one major player at work: gravity. Tiny differences in the density of matter, left behind from an earlier time of rapid cosmic inflation, began to pull things together slowly. Denser areas pulled in more gas and dark matter. Over vast stretches of time, these small ripples grew into huge clouds. Some of these clouds eventually collapsed under their own gravity, igniting the first stars and quasars, brilliant beacons of light that lit up the cosmos. These first lights were incredibly powerful. They started to break apart the neutral hydrogen gas that had filled the universe for so long, turning it back into charged particles. This process, called reionization, flooded the universe with ultraviolet radiation and marked the end of the Dark Ages. This new era, the epoch of reionization, began somewhere between 150 million and 1 billion years after the Big Bang. As time passed, gravity continued to do its work, slowly but surely building up more and more structure. The slightly denser areas of gas and dark matter kept pulling in more material. Eventually, these growing clumps formed the first galaxies, huge collections of stars, gas, and dust. Galaxies grouped together into galaxy clusters, and those clusters joined to form even bigger superclusters. Over time, all of this structure formed a vast network known as the cosmic web, a beautiful, gigantic pattern of filaments and voids, where galaxies are arranged in long strands separated by enormous empty spaces. None of this would have been possible without dark matter, a strange, invisible kind of matter that doesn't give off light or interact with ordinary atoms but has gravity. Dark matter acts like the scaffolding of the universe, helping regular matter gather and form stars and galaxies. Without it, the large-scale structures we see today would never have formed. Then, in the last few billion years, something surprising happened. Astronomers studying distant exploding stars, called supernovae, in the late 1990s made a shocking discovery. The universe's expansion wasn't slowing down like everyone expected. It was actually speeding up. Something was pushing everything apart. This mysterious force is now known as dark energy. Unlike dark matter, which helps bring things together, dark energy acts like an anti-gravity force, making the fabric of space stretch faster and faster. No one knows exactly what dark energy is. It might be a fundamental property of space itself, or it could be something entirely new, some strange energy field we don't yet understand. But today, dark energy makes up most of the energy in the entire universe. Its effects are so powerful that they now dominate the universe's behavior. If dark energy keeps working the way it does now, or gets even stronger, the universe will continue to expand faster and faster. In the far future, galaxies will drift so far apart that they'll no longer be able to see each other. Stars will eventually burn out, and the universe could become a cold, dark, lonely place. Even though the Big Bang theory is incredibly successful at explaining the history of the cosmos, it still doesn't answer everything. In fact, it leaves us with some of the biggest questions of all. The most puzzling mystery is this: what happened before the Big Bang? The theory explains how the universe grew from a very hot and dense beginning, but it doesn't tell us what started that beginning, or if anything existed before it. The idea of a singularity at the very start, a point where our current understanding of physics completely breaks down, is still one of the biggest challenges in cosmology. And then there's dark matter and dark energy. Together, they make up almost 95% of the universe, yet we still don't know what they are made of. We can see their effects, but we don't understand their true nature. Even the process of cosmic inflation, a rapid burst of expansion that likely happened just before the Big Bang as we know it, remains mysterious. It helps solve many problems in cosmology, but scientists are still working hard to understand what caused it, what kind of field or particle was responsible, and how it transitioned into the hot plasma that kicked off the Big Bang itself. The universe is filled with light, structure, and mystery, and even though we've come a long way in understanding its story, some of the most important chapters remain unwritten. One of the most important discoveries ever made in science is the realization that the universe is not fixed or unchanging. Instead, it is constantly growing. It is expanding all the time. This amazing idea changed the way we understand the entire cosmos. For thousands of years, many people believed that the universe had always been the same, that it was eternal and unmoving. But now, we know that the universe has a history, a beginning, and that it is still evolving. The evidence that the universe is expanding is strong and convincing. It comes mainly from detailed studies of light coming from distant objects in space, and from our deep understanding of how gravity and light behave. To truly understand how scientists discovered this, we need to look at the history of astronomy, the methods used to study the skies, and what this discovery tells us about the nature of everything around us. Before the 20th century, most scientists and thinkers believed the universe was static. It neither grew nor shrank. Even Sir Isaac Newton's famous laws of gravity had trouble explaining how a stable, unmoving universe could last forever. According to his laws, gravity would eventually pull everything together unless the universe was either infinitely large or perfectly balanced in every direction. But the idea of an infinite universe led to its own set of strange problems. Then, in the early years of the 20th century, Albert Einstein developed his groundbreaking theory of general relativity. This theory showed that gravity is not just a force, but actually comes from the bending or curving of space and time. However, Einstein's original equations did not describe a still, unchanging universe. They suggested that the universe should either be expanding or shrinking. At the time, this made Einstein uncomfortable, since the idea of a changing universe went against what most scientists believed. To fix this, he added an extra term to his equations called the cosmological constant. This term acted like a force that pushed outward, balancing gravity and keeping the universe static. Later in life, Einstein called this adjustment one of the biggest mistakes he ever made. Around the same time, a Dutch astronomer named Willem de Sitter discovered a different solution to Einstein's equations. He found that even in an empty universe, with no stars, planets, or galaxies, space could still expand on its own. This was a major clue that the universe might not be as still as people thought. But these early ideas were just theories. There was no real evidence yet to prove that the universe was expanding. The first solid step toward discovering the universe's expansion came from an American astronomer named Vesto Slipher. Beginning in the year 1912, Slipher began measuring the light from mysterious glowing clouds in space known as nebulae. Back then, scientists believed these nebulae were just gas clouds inside our own Milky Way galaxy. But something strange showed up in the light. Slipher found that the light from most of these nebulae was stretched out or shifted toward the red part of the spectrum. This effect, called redshift, meant that the objects were moving away from Earth. A few of the nebulae showed blue shift, meaning they were moving toward us. By the year 1917, Slipher had measured the speeds of 25 nebulae, and most were rushing away at very high speeds. Slipher didn't claim that this meant the whole universe was expanding, but his careful measurements laid the groundwork for one of the greatest discoveries in astronomy. Then came Edwin Hubble, another American astronomer. Building on Slipher's work, Hubble made two groundbreaking discoveries using the powerful 100-inch Hooker telescope at Mount Wilson Observatory in California. First, he looked closely at some of those spiral nebulae and discovered something astonishing. Inside the Andromeda Nebula, he found a type of star known as a Cepheid variable. These stars regularly grow brighter and dimmer over time, and their pattern of flickering is linked to their true brightness. By measuring how bright they appear from Earth, and comparing that with how bright they really are, Hubble could figure out how far away they were. When he calculated the distance to the Cepheids in Andromeda, he realized the nebula wasn't a part of our Milky Way at all. It was a separate galaxy, located far beyond the edge of our own. This discovery, made in the early 1920s, completely changed our view of the universe. For the first time, scientists understood that the Milky Way was just one of countless galaxies scattered across the vastness of space. Next, Hubble combined his new distance measurements with Slipher's earlier redshift data. In the year 1929, he published a stunning result. Galaxies that are farther away are also moving away from us faster. This became known as Hubble's law, and it showed for the first time that the universe was expanding. The farther away a galaxy is, the faster it seems to be flying away. This could be described with a simple equation. The galaxy's speed equals its distance multiplied by a number called the Hubble constant, which tells us how fast the universe is expanding. Hubble's discovery marked a turning point in science. It gave us the first clear observational proof that the universe is not standing still. It is growing larger with time. To understand why redshift is so important, think of how sound works. When an ambulance drives toward you, the siren sounds higher in pitch. As it passes and moves away, the pitch drops. This is called the Doppler effect, and it happens because the sound waves are squished when the ambulance comes closer and stretched when it moves away. Light behaves in a similar way. If a light source moves away, its light waves get stretched, making the light look redder. If it comes toward you, the waves are squeezed and the light looks bluer. But with very distant galaxies, the redshift is caused by something even stranger. Not by motion through space, but by space itself expanding. Think of dots drawn on a balloon. When you blow up the balloon, the dots move farther apart. They aren't moving by themselves, it's the balloon's surface that is stretching. In the same way, galaxies aren't speeding through space, they're being carried apart as the very fabric of space stretches. As light travels from a faraway galaxy, it moves through this expanding space, and the light waves stretch out too. The more space stretches while the light is on its way, the more the light gets redshifted. So when astronomers see highly redshifted galaxies, they're seeing light that left those galaxies a long time ago, when the universe was much younger and smaller. In the decades that followed, scientists found even more proof of the universe's expansion. A big breakthrough came from studying Type Ia supernovae, which are massive explosions that happen when a white dwarf star in a binary system gains too much material from its companion and explodes. These explosions always happen at the same mass, which means they all have nearly the same true brightness. Because of this, Type Ia supernovae can be used as standard candles, objects with known brightness that help astronomers figure out distances. By comparing how bright they look with how bright they really are, scientists can calculate how far away they are. In the late 1990s, astronomers used these supernovae to study galaxies billions of light years away. They expected to find that the universe's expansion was slowing down due to gravity. Instead, they were stunned to discover that the expansion was speeding up. This surprising finding led to the idea of dark energy, a mysterious force that appears to be pushing the universe apart faster and faster. No one knows exactly what dark energy is, but its effects are clear, and it now makes up about 70% of the total energy in the universe. The discovery of dark energy was a stunning confirmation that the universe is not only expanding, it is accelerating. From the first hints in Einstein's equations, to Slipher's early redshift data, to Hubble's clear observational proof, and finally to the discovery of accelerating expansion powered by dark energy, our understanding of the universe has come a long way in just over 100 years. What once seemed like a calm, eternal sky is now seen as a dynamic, restless cosmos, expanding, evolving, and full of secrets yet to be uncovered. The idea that our universe is expanding has incredibly deep and fascinating consequences, especially when we start thinking about the past. If space is growing larger today, that means it must have been much smaller a long time ago. If we keep tracing things backward in time, we eventually reach a moment when everything, all matter, energy, light, and even space itself, was squeezed into an unimaginably tiny, hot, and dense state. Scientists call this moment the Big Bang singularity, and it marks the beginning of everything we know: space, time, energy, and matter. It wasn't an explosion in space, it was the very beginning of space and time itself. This discovery changed everything. It meant that the universe wasn't always here in its current form. It's not eternal and unchanging. It's a living, evolving place. The fact that space is expanding tells us that the universe has a finite age. It had a starting point, and from that beginning, it's been growing and changing ever since. To figure out how old the universe is, astronomers look at how fast it is expanding. They use something called the Hubble constant, which tells us the rate at which galaxies are moving away from each other. By working backward, like rewinding the universe's growth, they can estimate when it all began. Early on, scientists used just the Hubble constant to do this, but over time they added more details, like how much matter the universe holds and the strange effects of something called dark energy, which seems to be speeding up the expansion. Thanks to these improvements, today's best estimates say that the universe is about 13.8 billion years old. That number agrees with many other kinds of measurements and evidence, which is a good sign that we're on the right track. But there's something really important to understand about this expansion. It's not that galaxies are flying through space like rockets. Instead, space itself is stretching, and the galaxies are being carried along with it, like raisins moving apart in rising dough. That's why galaxies that are very far away from us appear to be moving faster, not because they're travelling fast on their own, but because there's more space expanding between us and them. There are exceptions to this rule on smaller scales. For example, the Andromeda Galaxy, which is about 2.5 million light-years away, is on a collision course with our own Milky Way galaxy. This is because gravity is strong enough between them to pull them together, even though space is expanding. On the larger scale of galaxy clusters and beyond, though, the expansion wins, and galaxies keep drifting apart. Another mind-blowing idea is that the universe has no centre and no edge. Wherever you are in the universe, it looks like you're at the centre of expansion, because the stretching of space is happening everywhere equally. This supports a key scientific idea called the cosmological principle, which says that on very large scales the universe looks the same no matter where you are or which direction you look. In simpler words, the cosmos is both homogeneous, the same everywhere, and isotropic, the same in every direction. We also have powerful evidence for this expansion when we look deep into the night sky. Because light takes time to reach us, the farther away a galaxy is, the older the image we're seeing. When we observe very distant galaxies, we're actually seeing them as they were billions of years ago. And what do we find? These ancient galaxies were smaller, less organised, and often irregular in shape. Their stars formed at different rates, and their chemical makeup was different from galaxies today. All of this tells us that galaxies evolved over time, starting out simple and gradually becoming more complex. That's exactly what we'd expect in an expanding, evolving universe. Even more dramatic are quasars, brilliant blazing centres of young galaxies powered by gigantic black holes. We mostly see quasars at great distances, meaning they were more common in the early universe. This paints a picture of a cosmos that was once more energetic and chaotic than it is now. Still, not everything is perfectly settled. One of the biggest ongoing puzzles is about the exact value of the Hubble constant. Scientists have several ways of measuring it, using nearby stars, exploding supernova, or distant cosmic background radiation. But strangely, these different methods don't give exactly the same number. This disagreement is called the Hubble tension. It might just be due to tiny errors in our techniques, or it could mean there's something big we still don't understand about the universe. Some scientists think it could even point to new physics, beyond our current theories. That's why astronomers are using more powerful telescopes and better tools to keep studying the expansion of the universe. They hope not only to solve the Hubble tension, but also to better understand the mysterious dark energy that seems to be accelerating the expansion. This invisible force may hold the key to the universe's ultimate fate, whether it will go on expanding forever, becoming colder and emptier over time, or if dark energy will change and send the universe in a totally unexpected direction. If we could somehow rewind time and travel back to the very first moments of our universe's existence, we would find ourselves in a world that is utterly unlike anything we know. It would be a place of unimaginable heat and incredible density, filled with a seething, glowing mixture of the tiniest building blocks of matter. This strange early state of the universe is called plasma, a superhot soup made of particles so small we can't even see them with the most powerful microscope. This early chapter in the story of the cosmos is one of the most important. It acts as a bridge between the wild, extreme conditions just after the Big Bang and the moment when the very first atoms, the building blocks of everything we know, began to form. To truly understand how stars, galaxies, and eventually life came to exist, we must first understand this exotic phase of plasma, where the basic ingredients of matter were created and the rules of physics as we know them began to unfold. Immediately after the Big Bang, within just the first split second, the universe was not calm or quiet. Instead, it was a raging cauldron of energy and heat, where nothing as we know it could survive. If we zoom in on the moment just after the inflationary epoch, a period when the universe expanded faster than the speed of light, or perhaps even after the mysterious Planck epoch, when all the forces of nature were united, what we find is astonishing. There was no empty space, only a swirling storm of incredible heat and pressure. The temperature of the universe was not just hot, it was billions to trillions of degrees Celsius, far hotter than the core of any star that has ever existed. At such temperatures, atoms couldn't exist. Even the tiny nuclei at the center of atoms would be ripped apart instantly. Instead, the universe was filled with plasma, a state of matter in which particles are so hot they become ionized, meaning they carry electric charges. But this was no ordinary plasma. It was not the kind we see in neon signs or lightning bolts. It was far more exotic and intense. It was made up of protons, neutrons, electrons, and their antimatter twins, plus a staggering number of photons, the particles that make up light. In this early plasma-filled universe, energy was packed into every corner. Everything was so tightly squeezed together and so fiercely hot that particles were constantly smashing into each other, changing form and creating new ones. Light, or photons, had no room to travel. Every time a photon tried to move, it would crash into another particle, usually an electron, and bounce off or get absorbed. The universe was completely opaque, like being inside a glowing fog so thick that light couldn't get through. No matter how hard it tried, light couldn't escape. Even if an atom somehow managed to start forming, the energy of nearby photons was so powerful that it would instantly knock the electrons loose, breaking the atom apart again. This back and forth, atoms forming and then being destroyed, kept the universe in a chaotic plasma state for a long time. To understand what was happening during this time, we need to talk about the four fundamental forces of nature. These forces control everything in the universe. Gravity pulls things together and shapes galaxies, stars, and planets. Electromagnetism deals with electricity, magnetism, light, and the forces between charged particles. The strong nuclear force holds together the parts of an atom's nucleus, protons and neutrons. The weak nuclear force is responsible for certain types of radioactive decay and particle interactions. But in those earliest moments, these forces were not separate like they are today. Scientists believe they were all part of a single superforce. As the universe expanded and cooled, this superforce began to break apart into the separate forces we know now. First, gravity separated during the Planck epoch. Then the strong force broke away, followed by the splitting of the electroweak force into the electromagnetic and weak nuclear forces. The order and timing of these separations were incredibly important. They determined how particles would behave and combine in the plasma that followed. In the very beginning, during the first few millionths of a second, the universe was too hot for even protons and neutrons to exist. Instead, it was filled with a type of plasma made up of quarks, the particles that make up protons and neutrons, and gluons, the tiny messengers that hold quarks together. This quark-gluon plasma was unlike anything we see today. Quarks and gluons roamed freely, colliding, bouncing, and exchanging energy at unimaginable speeds. It was not until the universe cooled to about 1 trillion degrees Celsius that the strong nuclear force became strong enough to trap quarks together into stable combinations, protons and neutrons, in a process called hadronization. As things continued to cool, a very strange and critical event occurred: a battle between matter and antimatter. In those early moments, every time a particle of matter, like a quark or an electron, was created, an equal amount of antimatter, like an antiquark or a positron, was also formed. But matter and antimatter destroy each other when they meet. When they do, they vanish in a flash of energy, usually as light. If the universe had made exactly equal amounts of matter and antimatter, they would have completely wiped each other out. Nothing would remain. No stars, no galaxies, no planets, and no people. But for some reason, there was a tiny imbalance. For every 1 billion particles of antimatter, there were about 1,000,000,001 particles of matter. That tiny extra bit of matter, just one extra particle in a billion, is what survived. Everything we see in the universe today, from the smallest grain of sand to the largest galaxy, comes from that tiny surplus. After the protons and neutrons formed, the universe entered a new phase known as the lepton epoch. During this time, the universe was still extremely hot and full of energy, but now it was dominated by leptons, particles like electrons, positrons, and neutrinos, as well as photons. Eventually, electrons and positrons began to annihilate each other, just like quarks and antiquarks had earlier. Once again, a tiny excess of electrons survived, and those are the same electrons that make up the atoms in your body today. Neutrinos, on the other hand, are very different. They barely interact with anything at all. During this epoch, they slipped away from the rest of the plasma, spreading throughout the universe in a quiet, ghostly wave. This wave is called the cosmic neutrino background, and although it's still around us today, it is incredibly hard to detect. At this stage, the number of protons compared to neutrons was also set, which would later determine how the first atomic nuclei were formed in the next major phase, nucleosynthesis. For a very long time, from about 10 seconds after the Big Bang all the way to about 380,000 years, the universe was in what scientists call a radiation-dominated era. This means that most of the energy in the universe came from photons, not from matter. As the universe expanded, the light particles stretched out, their wavelengths getting longer and their energy decreasing. But during this long period, these powerful photons kept everything ionized. They had so much energy that atoms couldn't hold on to their electrons. This is why the universe stayed in a plasma state for such a long time. It was simply too hot and too energetic for stable atoms to form. Eventually, though, the universe cooled enough for electrons to finally combine with protons and neutrons, forming neutral atoms. When this happened, light could finally move freely, and the universe became transparent for the first time. That moment is called recombination, and it opened the door for the next chapters in the universe's story: galaxies, stars, planets, and life itself. But it all began with a storm of fire, light, and particles. A plasma-filled universe glowing in the darkness, setting the stage for everything that was to come. One of the most important events in the early life of the universe happened during a brief but crucial window of time, when the cosmos was still extremely hot and filled with a thick glowing soup of particles. This event is called Primordial Nucleosynthesis, also known as Big Bang Nucleosynthesis, or BBN for short. It took place when the universe was only between 3 and 20 minutes old, just moments after the Big Bang. By this point, the temperature of the universe had dropped from unimaginable extremes to about 1 billion degrees Celsius. That's still mind-blowingly hot, hotter than the core of any star, but it was finally cool enough for something extraordinary to begin: the fusion of basic particles. Protons and neutrons, which had been zipping around freely, could now start sticking together. This fusion process gave birth to the very first atomic nuclei. The first of these was deuterium, a special kind of hydrogen that has 1 proton and 1 neutron in its nucleus. Deuterium acted like a stepping stone. Once it formed, it quickly fused with other particles to create helium-3 and helium-4, both of which are different forms, or isotopes, of helium. A tiny amount of another element called lithium-7 was also created. However, the universe was cooling too fast. There wasn't enough time for heavier elements like carbon or oxygen to form during this phase. The universe had to wait much later, inside stars, for those to be created. The amounts of these light elements formed during BBN were not random. They depended very precisely on how many protons and neutrons were around, and how dense the universe was with ordinary matter, the kind that makes up atoms, planets, and people. Amazingly, when scientists today measure the amounts of hydrogen, helium, and lithium in the universe, Their observations match almost perfectly with what Big Bang nucleosynthesis predicts. This stunning agreement is one of the strongest pieces of evidence that the Big Bang theory is correct. Throughout all of this, from the time when the universe was still a sea of quarks and gluons, to the period of nucleosynthesis, the universe remained completely opaque, like a room filled with thick glowing fog. That's because electrons had not yet joined with atomic nuclei to form complete atoms. These free electrons roamed about, constantly bumping into photons, the tiny particles that carry light. Because of this, light could not travel very far. Any beam of light would be scattered almost immediately by an electron, like a flashlight trying to shine through dense smoke. This constant scattering meant the universe was filled with a hot, glowing fog made of charged particles and light, a place where light simply couldn't escape or travel freely. This is a defining feature of what we call the early universe plasma. Eventually, something remarkable happened. Around 380,000 years after the Big Bang, the universe had expanded and cooled even more. Its temperature had dropped to about 3000 Kelvin, which is similar to the surface temperature of a relatively cool star. This cooling led to a momentous change. The energy of the photons, the light particles, was now too low to keep tearing electrons away from atomic nuclei. Finally, electrons could settle down and join with protons and helium nuclei, forming complete neutral atoms. This process is known as recombination, though ironically it was the first time these particles combined, not a recombination. With electrons now safely bound into atoms, there were far fewer free charged particles for photons to bounce off. Suddenly, light was free. Photons could finally travel long distances without being stopped. This is known as photon decoupling, and it opened up the universe in a brand new way. The light from that moment still exists. It's stretched out and cooled, but we can detect it today as the cosmic microwave background or cosmic microwave background. This ancient glow is like a baby photo of the universe. It gives us a direct glimpse into what the cosmos looked like when it first became transparent. The cosmic microwave background is not perfectly smooth. It has tiny ripples, slight variations in temperature. These small irregularities represent the very first tiny clumps of matter, the seeds of galaxies. Over billions of years, gravity pulled more and more matter into these clumps, forming stars, galaxies, and the vast cosmic web we see today. This great transition, from an opaque, glowing fog to a transparent cosmos, marked the end of the radiation-dominated era and the beginning of the matter-dominated era. But even though light could now travel freely, there were no stars yet, no glowing objects lighting up the universe. This gave rise to a mysterious stretch of time known as the Cosmic Dark Ages, when the universe was silent and dark, waiting for gravity to gather the first stars into existence. In this way, the early universe plasma served as a cosmic forge, a crucible where the basic particles were formed, the fundamental forces began to separate, and the initial conditions were set for the birth of everything we know. From chaos and fire came order, light, and eventually life. In the very first moments after the birth of the universe, everything was pure energy, blazing, wild, and chaotic. There were no atoms, no stars, and no galaxies. Even the smallest bits of matter that we now take for granted, like protons and electrons, had not yet formed. The universe had just exploded into existence in a sudden burst known as the Big Bang, and immediately after, it went through an unimaginably fast period of growth called inflation. Before this, there was something we call the Planck era, a time so mysterious and extreme that the usual rules of physics break down. Right after this lightning-fast expansion, the universe was like a boiling soup of pure energy and fundamental particles. This soup was blazing hot, with temperatures far higher than anything we could imagine, hotter than the center of any star. Inside it, tiny building blocks of matter began to emerge. This was a turning point, a moment when energy began to turn into real physical particles. Everything we see today, from stars to people, can trace its roots back to this transformation. To understand what happened during this time, we have to turn to quantum physics, which explains how particles behave at unimaginably small scales and under extreme conditions. In these early moments, light particles called photons had so much energy that they could create matter out of thin air. According to Albert Einstein's famous equation, E equals mc squared, energy can turn into mass and mass can turn back into energy. So, when a photon had enough energy, it could turn into a pair of particles. For example, an electron and its opposite twin, a positron. But if those two particles met again, they would annihilate, vanishing in a flash of energy and turning back into photons. This constant back and forth, creation and destruction, was happening all the time during the universe's earliest moments. As the universe kept expanding, it started to cool down. The temperature of the universe controlled which particles could appear. In the beginning, it was hot enough to create even the heaviest fundamental particles. But as it cooled, only lighter particles could continue being made. This meant that the universe was a kind of cosmic dance floor, where particles were being created and destroyed in perfect balance, what physicists call thermal equilibrium. At these extremely high temperatures, something else incredible may have been happening. Scientists believe that all the fundamental forces of nature, such as gravity, electromagnetism, and the strong and weak nuclear forces, may have once been unified into a single superforce. This is the idea behind what scientists call grand unified theories, or GUTS. According to these theories, in the earliest instance, especially during the Planck epoch, which lasted only a fraction of a second, gravity may have already split off from the other forces. As the universe cooled, the remaining forces began to break apart from each other one by one. For example, the strong nuclear force eventually separated from the electro-weak force, and this moment was crucial because it set the stage for the formation of protons and neutrons. Now, let's talk about the most important early building blocks of matter, quarks and leptons. These are called fundamental particles because they are not made of anything smaller, at least as far as we know. There are 6 different types of quarks: up, down, charm, strange, top, and bottom. Quarks also have a special kind of charge called color charge, which has nothing to do with actual color but rather describes how they interact with the strong nuclear force. Protons and neutrons, the particles that make up the center of atoms, are made from quarks. A proton is built from 2 up quarks and 1 down quark, while a neutron is made of 1 up quark and 2 down quarks. Leptons are another important group of particles. The most familiar one is the electron, which carries a negative electric charge. There are also heavier versions of the electron called the muon and the tau, along with 3 types of neutrinos: the electron neutrino, the muon neutrino, and the tau neutrino. These neutrinos are strange, ghostly particles that have no electric charge and interact so weakly with matter that they can pass through entire planets without hitting anything. In the first split seconds after the Big Bang, the universe was a thick, blistering soup made of quarks, gluons, and leptons, all zooming around freely with their antiparticles. This early state is known as quark-gluon plasma. In this plasma, quarks had not yet been locked inside protons or neutrons. The universe was still too hot, and the quarks had so much energy that the strong nuclear force couldn't hold them together. Instead, they moved around freely, bouncing off each other and exchanging gluons, which are the particles that carry the strong nuclear force. But this phase didn't last long, only for a tiny fraction of a second. As the universe kept stretching out and cooling down, the temperature finally dropped to around 1 trillion degrees Celsius. At this point, something huge happened. The strong nuclear force became strong enough to trap quarks together, locking them into protons and neutrons. This moment is called hadronization. From then on, quarks could no longer exist freely. They had to combine into larger particles called hadrons. Among the hadrons, the most important ones were protons and neutrons, which are known as baryons because they are made of 3 quarks. But there was still a mystery, maybe the biggest of all. According to what we know, the Big Bang should have created equal amounts of matter and antimatter. For every quark, there should have been an antiquark. For every electron, a positron. If things had stayed exactly balanced, all the particles and antiparticles would have met and annihilated each other, leaving behind nothing but light, just a sea of photons. In that case, no stars, no galaxies, and no people would ever have formed. But clearly something tipped the scale. For some reason, there was a tiny imbalance, just a little more matter than antimatter. This tiny leftover of matter, perhaps just 1 extra particle of matter for every billion pairs, was enough to build everything we see today. In the year 1967, a brilliant physicist named Andrei Sakharov laid out 3 key conditions that would be necessary for this imbalance, called baryogenesis, to happen. Baryon number violation. There must be processes that can create or destroy baryons like protons and neutrons, instead of always keeping their numbers fixed. C and CP violation. The laws of physics must treat matter and antimatter differently in some way, especially when mirrored or reversed in time. Out of equilibrium conditions. The universe had to be changing so quickly, expanding and cooling, that particles couldn't keep up, allowing asymmetries to freeze in before they were erased. Many different theories try to explain this, including some based on grand unified theories or involving electroweak baryogenesis, but the full answer is still unknown. What we do know is that this slight imbalance made all the difference. It gave us a universe filled with matter instead of one made only of light. As the universe continued to cool, the leftover protons and neutrons began to settle down, but electrons and positrons were still everywhere, being made and destroyed by high-energy photons. Eventually, the universe cooled below the energy needed to keep creating these pairs. At that point, the final wave of annihilation happened, and just like with quarks, a small surplus of electrons remained. These surviving electrons would one day become part of atoms, orbiting around the nuclei made of protons and neutrons. Meanwhile, neutrinos, those nearly invisible particles, had already stopped interacting with other matter. They had decoupled from the rest of the universe much earlier and now travel silently through space. Today, this ancient sea of neutrinos, called the cosmic neutrino background, still exists, but it is so faint that it is nearly impossible to detect. It is one of the last whispers from the Lepton epoch, a time when particles danced through fire and light in the infant universe. In the very early moments of the universe, one of the most important things that happened was the setting of the balance between 2 key building blocks of matter, protons and neutrons. This delicate balance would later determine how the very first light elements, like hydrogen and helium, were formed. At first, when the universe was unimaginably hot, much hotter than the centre of any star, the forces of nature were incredibly active, especially the weak nuclear force, which helps particles change from one form into another. During this early stage, protons and neutrons could easily transform into each other. A proton, for example, could turn into a neutron by grabbing a positron, a positively charged version of an electron, and releasing a neutrino, an almost massless ghost-like particle. On the other hand, a neutron could break down into a proton, an electron, and a tiny particle called an antineutrino. These reactions happened so frequently that, for a while, the number of protons and neutrons stayed about the same. But as the universe expanded, it also began to cool, and as it cooled, these particle-changing reactions began to slow down. Eventually, they became too rare to keep the balance going. Since neutrons are slightly heavier than protons, they began to decay more often, turning into protons, electrons, and antineutrinos. This caused the number of neutrons to gradually decrease compared to protons. By the time the universe was around 1 second old, the temperature had dropped to about 10 billion degrees Celsius. At this point, the weak nuclear interactions had become too slow to keep up, and the swapping of protons and neutrons more or less stopped. This is known as the freeze-out of weak interactions. From that moment on, the number of neutrons compared to protons was fixed at about 1 neutron for every 6 or 7 protons. This particular ratio turned out to be incredibly important. Why? Because almost all the remaining neutrons would soon end up locked inside helium nuclei, each one made of 2 protons and 2 neutrons, during a process known as Big Bang nucleosynthesis, which would take place a few minutes later. Meanwhile, the extra protons that didn't pair with neutrons became the foundation for nearly all the hydrogen atoms in the universe. This early decision in the cosmic script set the stage for everything that followed, including the formation of stars, galaxies, and planets. At that time, the universe was still a hot, dense sea of particles, made mostly of free protons, free neutrons, and free electrons. It was also packed with high-energy photons, particles of light that carried enormous amounts of energy. These photons were so energetic that they couldn't allow any atoms to form. Instead, they constantly collided with the charged particles, especially electrons and protons, keeping everything in a glowing, foggy state. This period is called the radiation-dominated era because light, not matter, held most of the energy in the universe and controlled how fast the universe was expanding. So, in this early cosmic phase, the universe hadn't yet formed atoms or stars, but something just as important had happened. The basic ingredients of matter had been created and their numbers had been set. This primordial soup of particles and light laid the foundation for everything that would come next in the story of the universe. Without this careful balance between protons and neutrons, and the dominance of radiation in shaping the universe's behaviour, the cosmos as we know it would have turned out very differently. The story of how our universe changed and evolved is like an ancient tale written in the language of atoms and light. It began with a hot, dense sea of tiny particles, protons, neutrons, electrons and photons, all swirling together in an incredibly energetic state. From this fiery chaos, something extraordinary happened, the birth of the very first atomic nuclei. This event is known as Big Bang Nucleosynthesis for short, and it took place just a few short minutes after the universe itself came into existence. This moment in cosmic history is extremely important. Why? Because it explains why we see the lightest elements, hydrogen, helium, and lithium, scattered all across the cosmos in just the right amounts. These elements were not made in stars like heavier ones were. Instead, they were created quickly and efficiently in the first glowing moments of the universe's life, under very specific and extreme conditions. For this early process of nucleosynthesis to begin, the universe had to be in just the right state. It needed to be hot enough for particles to crash into one another and fuse, just like in the core of a star, but also cool enough so that the new atomic nuclei didn't get instantly torn apart by energetic light particles, known as photons. This delicate balance was achieved when the universe was about 3 minutes old, and it lasted for only 17 minutes, until the universe was roughly 20 minutes old. During that brief and critical window, the temperature dropped to about 1 billion degrees Celsius. That's still unimaginably hot, but compared to earlier moments, it was just cool enough to allow nuclear building blocks to stay together. The density of the universe also mattered a lot. It had to be high enough so that protons and neutrons could collide often and form nuclei, but not so high that all the neutrons were immediately used up in reactions. Luckily, the steady expansion and cooling of the universe helped create and then shut down this window of opportunity at just the right time. At the start of Big Bang nucleosynthesis, the universe was mostly made up of free protons and neutrons, surrounded by a sea of electrons and photons. A proton is basically the nucleus of a hydrogen atom, the simplest and lightest of all elements. A neutron is slightly heavier and is not stable on its own. When left alone, a neutron will naturally decay into a proton, an electron, and a tiny particle called an antineutrino. This decay happens with a half-life of about 10 minutes. Before nucleosynthesis began, there was a constant back and forth happening between protons and neutrons. Thanks to the weak nuclear force, protons could turn into neutrons and vice versa. These reactions kept the number of each type balanced, but as the universe expanded and cooled, the weak force lost its grip. By the time the universe was just 1 second old, the temperature had dropped to about 10 billion degrees Celsius, and these proton-neutron conversions slowed down dramatically. Because neutrons are heavier and naturally decay, there ended up being fewer of them. For every 1 neutron, there were about 6 or 7 protons. This 1:7 ratio was incredibly important. It would go on to determine how much helium could form. If there had been more neutrons, more helium would have been made. If there had been fewer, less helium would exist today. This fine balance helped shape the chemistry of the entire universe. But even with the right number of protons and neutrons, building atomic nuclei wasn't easy. The very first step was creating deuterium, which is a special kind of hydrogen with 1 proton and 1 neutron. Deuterium is fragile, like trying to stack cards during a windstorm. In those first minutes, the universe was still so hot that any deuterium formed would be instantly shattered by photons. Scientists call this problem the deuterium bottleneck. It wasn't until the universe cooled down to around 1 billion degrees Celsius, about 3 minutes after the Big Bang, that deuterium nuclei finally became stable enough to survive. Once this happened, everything changed. Like floodgates bursting open, nuclear fusion began in earnest. Deuterium started to combine with protons to form helium-3, or with other deuterium to create either helium-3 plus a neutron, or tritium, another hydrogen isotope with 1 proton and 2 neutrons. These lighter nuclei quickly fuse to form helium-4, a very stable form of helium made of 2 protons and 2 neutrons. Because helium-4 is so stable, and the fusion reactions were so efficient, nearly every neutron that had survived decay got locked into a helium-4 nucleus. This led to an astonishing outcome. By the time Big Bang nucleosynthesis ended, the universe had a primordial mix of about 75% hydrogen and 25% helium by mass. This amazing prediction, based purely on early universe physics, matches almost perfectly with what astronomers observe today. But the story doesn't end there. Although hydrogen and helium were the main products, a tiny amount of other light elements were also formed, most notably lithium-7. This came from rare fusion reactions, such as helium-4 fusing with tritium, or from the decay of beryllium-7 into lithium-7. However, the universe wasn't able to make much lithium, and it certainly couldn't make anything heavier. Why not? Because there are no stable atomic nuclei with 5 or 8 particles inside. This creates a kind of mass gap in nuclear fusion. So even if a helium-4 nucleus tried to fuse with a proton or a neutron, the result would be unstable and fall apart. To go beyond this limit to build elements like carbon, oxygen, and iron requires a much calmer, more stable environment, with high pressure and heat lasting millions or billions of years. That environment is found inside stars, not in the fast-cooling universe of the Big Bang. So in just under 20 minutes, the universe wrote the opening chapter of the periodic table. It created nearly all of the hydrogen and helium we see today, along with tiny sprinkles of lithium. The rest, the gold in our jewellery, the oxygen we breathe, the calcium in our bones, would come much later, from the hearts of stars and the explosions of dying suns. The predictions made by Big Bang nucleosynthesis, the process that created the universe's first light elements, are not just ideas written down in theory books. They have stood up impressively to the test of real-world observation. In fact, scientists have found that the actual amounts of these early elements seen across the cosmos match the predictions incredibly well. To check how much of these light elements were made in the early universe, astronomers try to study regions of space that have remained mostly untouched since the beginning. These are places that haven't been heavily changed or polluted by newer elements made later in stars. The best environments for such studies are ancient dwarf galaxies or faraway clouds of gas that contain almost no heavy elements, meaning they're as close as we can get to the original makeup of the universe. For example, astronomers measure the amount of deuterium, a heavier version of hydrogen, by observing the light from extremely distant quasars. As this light travels through clouds of ancient gas on its way to Earth, it leaves behind special fingerprints called absorption lines. These lines reveal how much deuterium is in those clouds. To find out how much helium-4 was created, scientists look at blue compact dwarf galaxies. These are small galaxies where very few stars have formed, so their gas has hardly been altered. They're perfect for measuring how much helium-4 came straight from the Big Bang. As for lithium-7, its tiny traces are detected in the atmospheres of some of the oldest stars in the Milky Way's outer halo. These stars are thought to have formed from gas that was almost completely untouched since the universe's earliest days. What's truly remarkable is that the observed amounts of hydrogen, deuterium, helium-3, helium-4 and lithium-7 all line up beautifully with the precise amounts predicted by Big Bang nucleosynthesis. This matches one of the strongest pieces of evidence we have that supports the idea of a hot, dense beginning for our universe, what we call the Big Bang. But the success of Big Bang nucleosynthesis doesn't end there. It also helps scientists figure out some of the universe's most important numbers, its fundamental physical properties. One example is the density of ordinary matter, which scientists call baryonic matter. The predicted amounts of the light elements depend on how much of this matter was present in the early universe. So by comparing the actual observed amounts of these elements with the predictions, scientists can calculate how much ordinary matter there is in the cosmos. And what's amazing is that this number matches perfectly with results from a completely different method. Studies of the cosmic microwave background, the faint glow left behind from the early universe. This agreement between two entirely separate lines of evidence gives scientists great confidence that they're on the right track in understanding the basic structure of the universe. Big Bang nucleosynthesis also gave early hints about how many types of light neutrinos, ghostly, nearly massless particles, exist in nature. Long before laboratory experiments could confirm it, BBN calculations strongly pointed to there being exactly 3 types of light neutrinos. Later, particle physics experiments backed this up, proving just how powerful BBN theory really is. However, not everything is perfectly understood. One mystery remains, and it's known as the lithium problem. When scientists measure the amount of lithium-7 in those ancient stars, they consistently find less than expected, only about 1/2 to 1/3 of the predicted amount. This difference is puzzling and still not fully explained. There are a few possible reasons for this lithium discrepancy. It could be that our models of how stars work, especially how their atmospheres affect lithium, are not quite right. Another idea is that something new and unknown in physics might be changing the way lithium was created or destroyed in the early universe. Or maybe there are hidden errors in how we understand the nuclear reactions that produced lithium in the first place. Whatever the cause, this problem remains an active area of research. Even with this one unresolved issue, the overall match between the predictions of Big Bang nucleosynthesis and the observed amounts of hydrogen and helium is so strong that BBN remains one of the key pillars of modern cosmology. The bare nuclei formed during this process, mostly hydrogen and helium, became the raw material for nearly all the visible matter in the universe. These hot charged particles stayed in a plasma state until the universe had cooled enough for electrons to join them, forming neutral atoms. That moment marked the beginning of the cosmic dark ages, a time before stars and galaxies had formed, and set the stage for everything that followed in the universe's grand story. The cosmic microwave background is one of the most powerful clues we have that supports the Big Bang theory, the idea that our universe began from an extremely hot and dense state, and has been expanding ever since. The cosmic microwave background is like a soft, ancient glow that fills the entire universe. It is not something we can see with our eyes, but with special instruments, scientists can detect this faint microwave light coming evenly from every direction in space. This light is actually a snapshot of the universe when it was still very young, only about 380,000 years old. It's like looking at a baby photo of the universe itself. The discovery and careful study of this glow have completely transformed how we understand the origin, evolution, and structure of the universe. It has revealed deep secrets about what the universe is made of, how it behaves on the largest scales, and how it came to look the way it does today. Long before anyone had the tools to detect this glow, a few brilliant physicists had already predicted its existence. In the late 1940s, during the middle of the 20th century, 3 scientists, George Gamow, Ralph Alpher, and Robert Herman, were working on ideas related to the early universe and how the first atoms formed. They believed that if the universe really did begin in a fiery explosion, the Big Bang, then it must have been filled with intense heat and light in the beginning. As the universe expanded and cooled over billions of years, they reasoned that some of that light would still be lingering today, though much colder and stretched into longer wavelengths, specifically microwaves. They even made an estimate. This ancient light should now have a temperature of just a few degrees above absolute zero, the coldest temperature possible, where all motion stops. According to their theory, during the early universe, matter and light were trapped together in a super-hot soup of particles, constantly colliding and interacting. This made the universe opaque, like looking through thick fog. But as the universe kept expanding and cooling, there would come a time when light could finally escape and travel freely. That moment would leave behind a distinct fingerprint on the radiation. This is what scientists now call the surface of loss scattering. Even though the theory was out there, no one had actually found this radiation until 2 American scientists, Arno Penzias and Robert Wilson, stumbled upon it by accident in the year 1964. They were not even looking for it. The 2 men were working at Bell Telephone Laboratories in Holmdel, New Jersey, testing a large horn-shaped antenna designed for satellite communication. Their task was to measure faint radio waves bouncing off communication balloons in space. But no matter where they pointed the antenna, they kept picking up a strange, constant background noise, like a soft hiss or static, that seemed to be coming from everywhere in the sky. This hiss matched a temperature of about 3.5 Kelvin, just a few degrees above absolute zero. They checked everything. They cleaned the antenna, removing droppings from pigeons nesting inside, thinking maybe that was causing interference. They tested for radio signals from cities, for military transmissions, even for radar. But the hiss wouldn't go away. It was always there, constant and uniform in every direction. At the same time, a team of scientists at Princeton University, led by Robert Dick, was working on building an antenna to detect exactly the kind of cosmic radiation that Gamow, Alpha and Herman had predicted. When Penzias and Wilson contacted them to ask about the mysterious signal they had found, Dickey immediately realised what had happened. Turning to his team, he famously said, "Boys, we've been scooped." That unexpected hiss was indeed the cosmic microwave background, the quiet afterglow of the Big Bang. This accidental discovery became one of the most important confirmations of the Big Bang theory ever made, and it earned Penzias and Wilson the Nobel Prize in Physics in the year 1978. The cosmic microwave background isn't just important because it exists. It's also about the details of how it behaves. It has some remarkable features that match exactly what scientists expect from a universe born in a fiery explosion. Firstly, the cosmic microwave background follows what's known as a blackbody spectrum. A blackbody is a perfect absorber and emitter of radiation. The fact that the cosmic microwave background fits this pattern so perfectly means that it came from a time when the universe was in thermal equilibrium, a state where everything was balanced in terms of energy. This confirms that the early universe was indeed extremely hot and dense, just as the Big Bang theory describes. Secondly, the temperature of the cosmic microwave background has been measured with incredible precision. It is about 2.725 Kelvin, which is just under 3 degrees above absolute zero. That very cold temperature is the result of over 13.8 billion years of cosmic expansion, which has stretched the once intense light into the microwave part of the spectrum. Thirdly, and perhaps most strikingly, the cosmic microwave background is almost perfectly uniform across the entire sky. No matter where we look, the temperature varies only very slightly. This evenness shows that the universe, in its earliest moments, was incredibly smooth and well balanced on large scales. This observation supports the cosmological principle, which says the universe looks roughly the same everywhere and in every direction. The cosmic microwave background is a direct witness to one of the most dramatic transitions in cosmic history, a moment called the recombination epoch, or the surface of last scattering. Before this moment, the universe was like a thick glowing fog. It was so hot, about 3000 Kelvin, that atoms couldn't form. Electrons and atomic nuclei existed separately, and light kept bouncing off the free-floating electrons, never getting far. But as the universe cooled, something wonderful happened. Electrons slowed down enough to combine with protons and helium nuclei, forming neutral atoms. Suddenly the fog lifted. Light could travel freely for the first time. The universe became transparent. The light released at that moment is still traveling today, stretched out and cooled by the ongoing expansion of space. That ancient light is what we now detect as the cosmic microwave background. So when we look at the cosmic microwave background, we are literally looking back in time to the moment the universe became clear. The existence and the specific features of the cosmic microwave background are not just pieces of evidence, they are cornerstones of modern cosmology. The fact that it has a perfect blackbody spectrum and a temperature of about 2.725 Kelvin matches precisely what we would expect from the cooled-down glow of a hot, dense beginning. Its uniformity across the sky supports the idea of a smooth, early universe, which later gave rise to galaxies, stars, and planets. Perhaps most importantly, the discovery of the cosmic microwave background helped to disprove the steady-state theory, an older idea which claimed that the universe had no beginning and looked the same forever. That theory could not explain the existence of the cosmic microwave background at all. The Big Bang theory, on the other hand, explains it beautifully. Although the cosmic microwave background appears to be almost the same in every direction, its real power lies in the tiny differences hidden within that smooth glow. When it was first discovered by Arno Penzias and Robert Wilson in the year 1965, the cosmic microwave background seemed nearly completely uniform, a soft, even afterglow of the Big Bang spread across the entire sky. But scientists believed there had to be small temperature differences hidden in that glow. These tiny variations were crucial, because without them, the universe would have remained too smooth. Gravity would have had nothing to work with, no slightly denser spots to pull more matter toward. and as a result, galaxies, stars, and planets might never have formed. Then, in the year 1992, something incredible happened. A satellite called the Cosmic Background Explorer looked at the whole sky with careful precision. It made a groundbreaking discovery. It found the first clear signs of those long-predicted tiny temperature differences in the cosmic microwave background. These variations were incredibly small, only about 1 part in 100,000, but they were exactly what scientists had hoped to see. These faint ripples were the very first signs of structure in the young universe. They showed where the early universe was just a little bit denser or cooler than average, little seeds from which everything we see today would eventually grow. The importance of these variations, or anisotropies, cannot be overstated. They are a direct snapshot of how uneven the universe was at the time when the cosmic microwave background was released, which happened when the universe was about 380,000 years old. In the slightly denser regions, temperatures were a little higher. In the less dense areas, they were a bit cooler. These small differences mattered because gravity works more strongly in denser places. Over billions of years, these regions pulled in more and more matter, forming stars, galaxies, and massive clusters. Meanwhile, the underdense regions lost matter and became the vast empty spaces we now call cosmic voids. This process of gravitational imbalance was like a chain reaction. Tiny bumps became bigger and bigger structures as time went on. Even more excitingly, these anisotropies gave powerful support to the theory of cosmic inflation. This is the idea that, in the very earliest moments of the universe, far less than a second after the Big Bang, space itself expanded unimaginably fast. Inflation would have stretched out tiny quantum fluctuations to enormous scales. The tiny differences we see in the cosmic microwave background today are exactly the kind of pattern we would expect if that inflation had really happened. In short, these faint ripples in the cosmic microwave background are like fingerprints left behind by the universe's most ancient processes. After Cosmic Background Explorer's success, newer satellites were sent into space to study the cosmic microwave background in even greater detail. One of the most important was the Wilkinson Microwave Anisotropy Probe, or WMAP, which launched in the year 2001. WMAP gave us much sharper and clearer maps of the temperature differences in the cosmic microwave background. It confirmed everything Cosmic Background Explorer found, and went even further by revealing more detailed patterns across the sky. Then, in the year 2009, the European Space Agency launched the Planck satellite. Planck created the most detailed map of the cosmic microwave background ever made. With unmatched resolution and sensitivity, it measured the tiniest temperature variations across the entire sky. Thanks to missions like these, scientists could now study the cosmic microwave background's patterns in exquisite detail and begin to unlock deep secrets about the universe. It turns out that the patterns in the cosmic microwave background are not just random. They contain a huge amount of information about how the universe works. Scientists study what's called the cosmic microwave background power spectrum, a kind of graph that shows the strength of the temperature variations at different scales. These peaks and valleys in the graph represent acoustic oscillations, or sound waves, that rippled through the hot plasma of the early universe before it became transparent. At that time, matter and radiation were closely linked. When photons, the particles of light, interacted with the charged particles in the plasma, they created pressure waves. When the universe finally cooled enough for atoms to form, these sound waves were frozen into place. Their imprint remained in the cosmic microwave background, like ripples frozen on the surface of a pond. By analysing where the peaks and troughs appear in the spectrum, scientists could calculate the most fundamental properties of the cosmos. From this, we now know with high confidence that the universe is almost perfectly flat, meaning that space does not curve much in any direction, and parallel lines remain parallel. This is one of the most profound findings in all of cosmology. We also know that the universe is around 13.8 billion years old, and that it is expanding at a measurable rate. The cosmic microwave background also tells us how the universe is made, roughly 5% ordinary matter, like stars, gas, and planets, about 27% dark matter, a mysterious invisible substance that does not emit light, and a whopping 68% dark energy, a strange force that drives the universe to expand faster and faster. But the cosmic microwave background doesn't just tell us about temperature. It also tells us about polarization, a special property of light. Just like sunlight can be polarized when it reflects off water, the light from the cosmic microwave background is slightly polarized too. There are two main kinds of polarization: E modes and B modes. E modes are created by the same density variations that form the temperature patterns, and they have been clearly detected. B modes are much harder to detect. They can come from two sources. One is from the twisting and bending of E modes as they pass through galaxies and clusters. This is called gravitational lensing. The other, much more exciting possibility is that B modes might be caused by primordial gravitational waves, ripples in spacetime created during the inflationary period. If we ever detect these original B modes clearly, it would be like hearing the faint echoes of the universe's birth cry. It would give us direct evidence of inflation and a window into the highest energy physics imaginable. So far, we have detected lensing B modes, but the search for the original inflationary ones is still ongoing, one of the most thrilling frontiers in cosmology. In many ways, the cosmic microwave background map is like a baby picture of the universe. The hotter spots in the map show places where the universe was just a little denser, which would grow into galaxies and clusters. The colder spots were less dense and would become vast, empty regions. The cosmic microwave background marks the earliest moment in time we can actually see, because before that, the universe was full of a glowing, opaque plasma. Any light emitted earlier than the cosmic microwave background would have been scattered endlessly, never reaching us. Because of all this, the cosmic microwave background has become one of the most powerful tools in all of cosmology. It tells us not only about how the universe began, but also about what it is made of, how it is shaped, how fast it is growing, and what its future might be. The study of the cosmic microwave background continues to guide our understanding of the cosmos, shining light, literally, on the most ancient and mysterious moments of our universe's existence. At the moment of its birth, the universe looked surprisingly smooth and even, like a calm ocean without waves. This ancient snapshot comes from the cosmic microwave background. The cosmic microwave background reveals what the universe looked like when it was only 380,000 years old. Back then, everything was spread out almost perfectly evenly, with only the tiniest bumps and dips in density, so small they were barely noticeable. Yet when we look at the universe today, we see something completely different. We see stars grouped into galaxies, galaxies gathered into clusters, and those clusters arranged into giant chains and walls, all part of a colossal structure called the cosmic web. These structures stretch across the entire universe, separated by vast, empty spaces known as voids. So how did we get from a smooth, almost featureless beginning to this incredibly rich and clumpy universe? This transformation is one of the most fascinating mysteries in all of cosmology. The science of how the universe began and evolved, and the main force that turned tiny differences in the early universe into the grand structures we see today is gravity. Like a master sculptor, gravity used the tiny imperfections in the early universe, tiny spots where the density was ever so slightly higher or lower than average, as the seeds for galaxies, stars, and everything else. If the universe had been perfectly smooth at the time the cosmic microwave background was released, there would have been no galaxies, no stars, no planets, nothing at all to break up the uniformity. Gravity would have had nothing to pull on. A perfectly smooth universe would have stayed that way forever, but luckily it wasn't perfect. There were minuscule irregularities, tiny patches just a little denser than others, and these were picked up in the cosmic microwave background as faint temperature fluctuations. These variations were extremely small, only about 1 part in 100,000, but they made all the difference. Where did these early fluctuations come from? The answer lies in a powerful idea called cosmic inflation. According to this theory, in the first tiny sliver of time, less than a trillionth of a second after the Big Bang, the universe expanded at an unbelievable speed. During this explosive stretching, quantum fluctuations, random jitters in energy at the tiniest scales, were stretched out to cosmic sizes. These quantum ripples became the slightly denser or emptier spots that eventually showed up in the cosmic microwave background and gave gravity something to work with. In a way, Inflation took the microscopic fuzziness of quantum physics and blew it up into the seeds of stars and galaxies. Once those seeds were in place, gravity began its long and careful work. In areas that were just a bit denser, gravity pulled in more matter. This made those spots even denser, which in turn made their gravitational pull stronger, attracting even more matter. This self-reinforcing cycle is called gravitational instability, and it allowed dense regions to grow over time, while less dense regions became emptier. Over billions of years, this process shaped the grand structures we now see. But there was another essential ingredient in this story: dark matter. This mysterious kind of matter does not shine or glow. In fact, it doesn't interact with light at all, which is why we call it dark. But even though we can't see it, dark matter has mass, and it responds to gravity. That means it played a crucial role in helping structure form in the universe. In the early universe, before recombination, the time when atoms first formed and the universe became transparent, ordinary matter was tightly linked with light. Photons, particles of light, kept bouncing off free protons and electrons, which prevented ordinary matter from clumping together. Any small lump would be quickly smoothed out by the intense pressure of the surrounding radiation. It was like trying to build a sandcastle in a stormy sea. The waves would immediately wash it away. Dark matter, however, was not affected by radiation in this way. Since it doesn't interact with light, it could start clumping together even before recombination. These early clumps of dark matter created gravitational wells, invisible valleys that ordinary matter would later fall into, once the universe had cooled enough and photons no longer pushed matter around. Without dark matter, the universe might still be smooth and nearly empty today. As time went on, these clumps of dark matter grew larger and formed what scientists call dark matter halos, huge invisible clouds of dark matter with powerful gravitational pull. We cannot see these halos directly, but we know they exist because they affect the way galaxies spin and how light bends around them, a phenomenon known as gravitational lensing. After recombination, when the universe was around 380,000 years old, ordinary matter was finally free to move without being pushed around by light. It began to fall into the gravitational wells created by dark matter halos. There, it collected, cooled, and eventually collapsed to form the first stars and galaxies. This process didn't happen all at once. It followed a hierarchical pattern, meaning that small structures formed first, then merged over time to form bigger ones. The first things to form were tiny clumps of dark matter and gas. Inside these, the first stars were born, the so-called population 3 stars. These stars were gigantic, burned very brightly, and lived only for a short time, but they were incredibly important because they helped reionize the hydrogen gas that filled the universe and paved the way for later generations of stars and galaxies. Those early clumps of stars merged to form small galaxies. Those small galaxies merged into larger galaxies. Over time, these galaxies gathered into groups, and those groups merged into massive clusters. Gravity kept building larger and larger structures, creating a grand cosmic architecture that grew more complex over billions of years. Eventually, the universe began to take on a shape that we now call the cosmic web, a vast and intricate network of matter stretched across the universe. Scientists have run huge computer simulations, using billions of particles to mimic how gravity shaped the universe over time. These virtual universes produce a cosmic web that looks remarkably similar to what we see when we map the real sky. The cosmic web is made up of 3 main parts: dense nodes where galaxy clusters live, long filaments where galaxies are strung together like pearls on a string, and enormous voids where hardly any galaxies are found. Galaxies are not scattered randomly across the universe. Instead, they are arranged along these filaments and gather at their intersections, the joints of the cosmic web. This pattern reveals the deep connection between the tiny fluctuations in the early universe and the magnificent structures we see billions of years later. In the vast and invisible framework of dark matter that stretches like a giant web across the universe, something remarkable began to happen. Inside these dark matter halos, huge clumps of unseen mass that act like invisible scaffolding, ordinary gas, made of atoms like hydrogen and helium, began to cool down. As this gas lost heat, It started to collapse inward under the force of gravity. As it squeezed tighter and tighter, it grew denser, until finally it became dense and hot enough to ignite the formation of stars. This marked the beginning of galaxy formation. But the story of how galaxies grow and change over time is far from simple. It is shaped by a beautiful and chaotic dance involving the birth of stars, the explosive deaths of massive stars and supernovae, the influence of enormous black holes at the centers of galaxies, and fierce galactic winds. Galaxies also bump into each other and merge, sometimes gently, sometimes violently, adding to the complexity. In the early universe, galaxies looked quite different from the graceful spirals and smooth ellipticals we see today. They were usually smaller, more uneven in shape, and contained fewer of the heavier elements that are created inside stars. Over billions of years, these small, irregular galaxies collided and combined. Each collision reshaped their structure, while new generations of stars gradually enriched their gas with heavier elements like carbon, oxygen, and iron. As galaxies gathered into larger structures, they formed vast families called galaxy clusters. These are the largest objects in the universe that are held together by gravity. A typical galaxy cluster might contain hundreds or even thousands of galaxies. But galaxies themselves are just the tip of the iceberg. Most of a cluster's mass is hidden in dark matter. Between the galaxies, hot gas left over from their dramatic past fills the space, glowing in X-rays and revealing clues about how these massive structures formed. Gravity is the main force behind all this structure. It pulls matter together, shapes galaxies, and binds them into clusters. But it is not the only force at work. On the larger scales, another strange and powerful influence must be considered: dark energy. Dark energy is a mysterious invisible pressure that seems to push space apart, causing the entire universe to expand faster and faster. While gravity dominates on small scales, like inside galaxies or clusters, dark energy becomes important when we zoom out to enormous distances beyond a few 100 million light-years. At those vast scales, dark energy starts to fight against gravity, slowing down the growth of the larger structures. It stops faraway galaxy clusters from merging into even bigger systems, and stretches space so much that some distant galaxies will eventually move so far away that their light can no longer reach us. They will disappear beyond our cosmic horizon, lost forever to the expanding universe. This tug-of-war between gravity, which pulls things together, and dark energy, which pushes things apart, will shape the future of the cosmos. It will determine whether galaxies keep merging and evolving, or whether the universe becomes so empty and stretched out that galaxy formation grinds to a halt. To explore these cosmic processes in more detail, scientists use powerful tools called cosmological simulations. These are enormous computer experiments that try to mimic how the universe grew over time. By using supercomputers, scientists can simulate how billions of invisible dark matter particles move and clump together under gravity. They start with the tiny ripples in matter that we see in the cosmic microwave background. The faint glow from when the universe was only about 380,000 years old, and run the simulation forward over billions of years. These simulations show how the cosmic web formed, how dark matter halos came together, and how galaxies gathered into clusters. They also help scientists test different theories about dark matter and dark energy, and see what kinds of galaxies might form under different cosmic rules. But simulations are not the only source of knowledge. Astronomers also look directly at the universe using huge surveys that map the positions of millions of galaxies, like the Sloan Digital Sky Survey. They observe how light from distant galaxies is bent and distorted by the gravity of dark matter, a method called weak gravitational lensing. They also use X-ray telescopes to study the hot gas inside galaxy clusters, revealing more about how these enormous structures formed and evolved. Together, simulations and observations have helped build a detailed picture of how the universe's structures came to be. But not everything fits perfectly. Some puzzles remain unsolved. For example, simulations predict that large galaxies like our Milky Way should have many more small companion galaxies than we actually see. This is known as the missing satellite problem. Another issue, called the cusp core problem, relates to how dense the centers of dark matter halos should be. Simulations suggest sharp peaks in density, but real galaxies often show flatter, gentler cores. Dark matter is a strange and invisible kind of matter that we can't see because it doesn't interact with light or any other kind of energy. We know it is there because of the odd effects it has on gravity, which can't be fully explained by the rules of physics unless there's more matter around than we can actually see. These strange effects show up when we study things like how galaxies form and change over time, how light bends around huge objects, called gravitational lensing, and even the way galaxies move within groups. We also notice its effect in the shape of the universe and the leftover energy from the Big Bang. In the most widely accepted model of the universe, known as the lambda CDM model, the universe's total mass and energy is made up of 5% regular matter, 26.8% dark matter, and 68.2% dark energy. That means dark matter makes up about 85% of the total mass, while dark matter and dark energy together make up 95% of the universe's total energy. We don't know exactly what dark matter is, but it doesn't seem to interact with regular matter or light, except through gravity, making it nearly impossible to find with the tools we have now. The main idea is that dark matter might be made up of tiny unknown pieces, such as weakly interacting heavy particles or axions. Another idea is that dark matter could be made of ancient black holes from the early universe. Dark matter can be sorted in different ways based on how fast its pieces move: cold, warm, or hot. Most scientists think dark matter is cold, meaning its pieces move slowly, letting them come together and form things over time. While most space scientists believe dark matter is real, some still question the idea. A small group of scientists, puzzled by certain things that regular dark matter doesn't fully explain, suggest that maybe the rules of gravity need to be changed. They've suggested other ideas like changed Newtonian motion or new kinds of gravity, but none of these ideas can fully explain all the proof we've found so far. This shows that, even if gravity needs some changes, dark matter still seems to be an important part of the puzzle. The idea of dark matter has a long and interesting past, filled with exciting findings and ideas that helped build our current understanding of the universe. The story begins with the work of some of the smartest minds in science, starting in the late 19th century. In the year 1884, William Thomson, better known as Lord Kelvin, made some interesting guesses. He talked about the possible number of stars around our Sun in a book based on a series of talks he gave in Baltimore. Kelvin was trying to guess the number of stars near the Sun. He did this by studying how stars moved around our solar system. Using this information, he wondered what would happen if there were 1 billion stars within a distance of 1 kiloparsec from the Sun. At this distance, the stars would seem to move in ways that were hard to explain, and this idea led to more thinking about invisible matter in space. Lord Kelvin also guessed the Sun's age to be between 20 and 100 million years, which was later shown to be wrong. But his curiosity about the stars and how they move helped start early ideas about dark matter. A couple of decades later, in the year 1906, the French math and science expert Henri Poincaré used the name dark matter, or matière obscure, while talking about Lord Kelvin's work. Poincaré said that there might be hidden matter in the universe, but he also thought that this hidden matter would be less than the matter we can see. Even though his ideas were far from correct, Poincaré's use of the term dark matter brought the idea into the science world. In the 1920s, dark matter continued to interest skywatchers. In the year 1922, Dutch sky expert Jacobus Kapteyn became one of the first to use how fast stars move to suggest the existence of dark matter. He noticed that the way stars moved in space could be affected by unseen forces, hinting that invisible matter might be there. Then, in the year 1930, Swedish sky expert Knut Lundmark went further with the idea, realizing that the universe must have much more matter than we could see through our telescopes. This finding was important because it showed that the part of the universe we can see might not be the whole story. In the year 1932, another Dutch scientist, Jan Wout, joined the talk by saying that dark matter might be in our part of the galaxy. Wout studied how stars moved near our galaxy and decided that there must be more matter in our galaxy than we could see. But later, he found out that his numbers weren't fully correct, and more study would be needed to truly understand this unseen matter. Then, in the year 1933, Swiss space expert Fritz Zwicky made a major finding while studying groups of galaxies at the California Institute of Technology. Zwicky was looking at the Coma cluster, a large group of galaxies, and noticed something strange. The galaxies in the group were moving much faster than expected based on the matter we could see. This led him to say there must be a huge amount of invisible matter, which he called Dunkel Materie. Zwicky guessed that the Coma cluster had around 400 times more matter than could be seen through telescopes, based on how the galaxies were moving. He believed that this unseen matter was causing the gravity that kept the galaxies in the group together. Even though Zwicky's numbers were far off, mainly because of old values, he was one of the first to correctly say that the universe must have unseen matter pulling things with gravity. Zwicky, however, had a different idea of dark matter than we do today. He thought that dark matter was just regular matter that didn't give off light, not something totally different like the strange dark matter we think about now. Still, his work was a big step toward discovering dark matter. As time went on, more signs of dark matter started to appear. One important piece came from studying how galaxies spin. In the year 1939, H.W. Babcock studied how the Andromeda Galaxy spins. He found that the stars on the outer sides of the galaxy were moving much faster than expected. This showed that there was much more matter in the galaxy than could be seen by just looking at the stars. At first, Babcock thought that this strange spinning might be because light was being blocked inside the galaxy, or because the galaxy worked differently in its outer parts. But his study was an early clue that something invisible was changing the way the galaxy spun. The next year, in 1940, Jan Oort made another big discovery. He studied a galaxy called NGC 3115 and found a large invisible cloud of matter around it. This was more proof that galaxies might have hidden matter we couldn't see with the tools we had at the time. The idea of dark matter really started to become popular in the 1970s. Many different science studies came together to show that galaxies might be surrounded by huge, invisible clouds of matter. In the year 1974, two different research teams, one from Princeton, New Jersey, led by Jeremiah Ostriker, Jim Peebles, and Amos Yahiel, and another from Tartu, Estonia, led by Jani Nasto, En Saar, and Ants Kasich, came to the same idea on their own, making the idea stronger. One big clue that pointed to these invisible galaxy clouds was the way galaxies spin. Both regular telescopes and radio telescopes were very important in these findings. Vera Rubin and Kent Ford, using a new tool called a spectrograph, made better measurements of the speed of edge-on-spiral galaxies and found surprising results in how they spun. At the same time, radio scientists used special radio telescopes to study the 21 centimeters signal of hydrogen gas in nearby galaxies. Unlike starlight, which only comes from the middle parts of galaxies, hydrogen gas spreads much farther out. This lets scientists watch spinning patterns much farther from the center, giving a better idea of how much matter was really in a galaxy. Early studies of the Andromeda Galaxy, using big telescopes like the 300-foot Green Bank telescope and the 250-foot Jodrell Bank dish, showed that the hydrogen spinning curve didn't behave as expected from Kepler's rules, which describe how things move around a center of gravity. As tools got better, more advanced equipment let scientists measure even farther. In the year 1975, Roberts and Whitehurst went even farther, measuring the spinning speed of Andromeda all the way out to 30 kiloparsecs. Their results showed that the galaxy's spinning stayed flat even far from the center. This was important because it meant there was much more matter out there, beyond what we could see with regular telescopes. These findings, shown in their graphs, combined starlight data with the new hydrogen data, clearly showing the surprising flatness of how the galaxy spun on the outside. The solid line in the graph showed the starlight data, while the other line showed the total matter, which kept growing even in the farthest parts of the galaxy. At the same time, scientists were coming up with even better ways to study galaxies. Using interferometric arrays, many radio telescopes working together, researchers like Rogstad and Shostak in 1972 mapped the hydrogen spinning curves of 5 spiral galaxies. They found that all of these galaxies had flat spinning curves as well, meaning that the mass in the outer parts of the galaxies was much more than what could be explained by the stars and light we can see. By the late 1970s, most people in the field agreed that dark matter halos probably surrounded galaxies, and this became one of the biggest puzzles in space science. In the 1980s and 1990s, many observations began to suggest that dark matter was real. One important study done by Persic, Salucci and Stell in 1996, looked closely at 967 spiral galaxies and found strong proof that dark matter exists. Other backup evidence included strange things like gravitational lensing, where galaxy groups bend light from things behind them, the spread of hot gas in galaxies and groups, and the way small temperature differences, called anisotropies, show up in the cosmic microwave background, which is the leftover glow from the Big Bang. Today, most scientists agree that dark matter is made up of particles that we haven't found yet, and these particles are unlike anything we already know. The search to find this strange particle has become one of the biggest goals in particle physics, with many scientists using different ways and experiments to try and figure out the truth. To put it simply, when scientists talk about matter in the universe, they are talking about anything that adds to the total energy, and its thickness changes in a certain way as the universe grows. Specifically, it gets thinner as the cube of the growth, meaning the more the universe stretches, the less matter there is in each area. This is not the same as radiation, which gets thinner even faster. Its energy gets weaker as the universe grows, following the opposite of the fourth power of the growth. On the other hand, the cosmological constant acts differently. It stays the same no matter how much the universe stretches, meaning its energy thickness stays constant. This difference in how matter, radiation, and the cosmological constant act is because of something called radiation redshift. To picture this, imagine the universe getting bigger. If the size of the universe we can see doubles, the scale factor of growth also doubles. Because of this, the energy of things like the cosmic microwave background radiation, the glow left over from the Big Bang, gets weaker because each light particle, photon, has to stretch out over a bigger space, lowering its energy. The same thing happens to very fast-moving particles, like the early neutrinos. They also lose energy in a similar way. But the cosmological constant, which is part of space itself, doesn't change no matter how much the universe expands. When we say dark matter, we're usually talking about parts of the universe that we can't see, but still have mass and follow similar rules as regular matter. However, more specifically, dark matter is often used to talk about a special kind of invisible matter that isn't made of the usual particles we already know, leaving out something called missing baryons. The meaning of dark matter can change depending on how it's used. The arms of spiral galaxies spin around their center, and as you move farther from the center, the amount of visible mass in the galaxy goes down. If all the galaxy's mass were visible, it would act like a simple system where most of the mass is in the center, and things move around it, like planets around the Sun in our solar system. Based on Kepler's third law, we'd expect these things to move more slowly the farther out they are, just like how the planets farther from the Sun move slower, but that's not what we see in galaxies. Instead, the spinning speeds of stars and gas in a galaxy stay the same, or even go up the farther out you go from the center. To explain this strange finding, it's clear that the spread of mass in spiral galaxies is not like the solar system. In fact, there may be a lot of invisible, non-glowing matter, what we call dark matter, on the edges of the galaxy. In systems that stay together, like galaxies, the stars also follow a rule called the virial theorem. This rule helps explain how mass is spread out in a system by looking at the speeds of the stars. When astronomers look at how fast stars are moving in systems like elliptical galaxies or tightly packed star groups, they can use this rule to figure out how the mass is spread out. But in many cases, the measured speeds don't match what we'd expect from the amount of visible mass in the system, even when we think about the star's complex orbits. Just like with the spinning curves of galaxies, the best way to explain this difference is that there's more invisible matter involved. Again, dark matter. Galaxy groups are very useful in studying dark matter because we can measure their mass in 3 different ways. By looking at how fast the galaxies in the group are moving, by studying the X-rays coming from the hot gas in the group. By studying these X-rays, we can find the temperature and thickness of the gas, which lets us figure out the pressure. Using the balance between gravity and pressure, we can find the total mass of the group. By using gravitational lensing, where the mass of the group bends light from things behind it. This lets us measure the group's mass without needing to see how its galaxies are moving. All 3 of these ways give us the same result. Dark matter makes up about 5 times more mass than all the matter we can see in these groups. One interesting result of Einstein's theory of general relativity is something called gravitational lensing. This happens when huge things, like galaxies or galaxy groups, sit between a light source and the person looking at it. These big things act like a lens, bending the light that passes through them, making the light from the source look bent or stretched. The key thing is that gravitational lensing only needs mass to happen. It doesn't matter what the mass is made of. The bigger the mass, the more it bends the light. For example, think of a galaxy group between us and a very far away object like a quasar. The group of galaxies will bend the light from the quasar, making it look different. When we talk about strong lensing, we mean the big, clear way light from background galaxies can bend into arc shapes as it goes through a large object's gravity field. This has been seen around many faraway galaxy groups, including one called Able 1689. By studying the shapes of these arcs, scientists can figure out how much mass the galaxy group has. In weak lensing, the bending is much smaller, and galaxies don't turn into arcs. Instead, we see tiny changes in their shapes. By studying these small changes, scientists can learn about how dark matter is spread across the universe. The patterns of mass and light in these studies match what we expect from dark matter studies. Now, while both dark matter and regular matter are types of matter, they act very differently. In the early universe, regular matter had electric charge and interacted a lot with light, which caused it to scatter. But dark matter doesn't interact with light, even though it still affects the universe in other ways. For example, it pulls on things through gravity, especially across huge distances, and changes how regular matter moves and spreads out. Because of these differences, regular matter and dark matter grow and change in different ways, leaving separate marks on the cosmic microwave background. The cosmic microwave background is almost like a perfect blackbody, meaning it gives off a smooth, even temperature. But there are tiny temperature changes, about 1 part in 100,000, that scientists can study. These small differences, called anisotropies, can be mapped out across the sky. When scientists turn this map into a graph called the angular power spectrum, they see a bunch of peaks that are evenly spaced but have different heights. The exact spots of these peaks depend on key things in space science, and by comparing these spots to ideas in theory, we can learn more about what the universe is made of. The first time scientists found these small changes in the cosmic microwave background was in 1992 using the COBE satellite, but it couldn't show the peaks clearly. In 2000, the Boomerang experiment, using a balloon to take readings, found the first of these peaks. Later, the WMAP satellite and the Planck spacecraft measured these peaks much more clearly. What they found agreed with the Lambda CDM model of space science. Structure formation is the process that began shortly after the Big Bang, when small, uneven parts in the universe's thickness caused matter to fall together and form stars, galaxies, and groups of galaxies. Before this time, the universe was even, with no big differences in thickness, as described by the Friedman answers to general relativity. Over time, tiny changes in thickness started to grow and stick together, turning the smooth, plain universe into a more detailed shape filled with stars and galaxies. In the early stages, light energy filled the universe and had a big effect on matter. This light energy stopped normal matter's thickness changes from growing and forming shape. If the universe only had normal matter, these changes would not have had enough time to grow into the galaxies and groups we see today. The key to fixing this problem lies in dark matter, which is not affected by light energy. This allowed its thickness changes to grow first, creating gravity wells that later helped normal matter fall into galaxies and other shapes. The pull from dark matter acted like a magnet, pulling in normal matter and speeding up the making of these large space shapes. A clear example of the effect of dark matter is the Bullet cluster, formed by the crash of 2 big galaxy groups. What makes the Bullet cluster especially interesting is the difference between where the mass of the group is found according to gravity bending, the bending of light around heavy objects, and where the matter we can see is found. This difference is hard to explain with other gravity ideas, which expect gravity bending to happen only around matter we can see. However, the usual idea of dark matter can easily explain this. The gas we can see in the groups, which reacts with light and other types of energy, was slowed down and cooled by electric forces during the crash. Dark matter, on the other hand, doesn't react with light in the same way, so it moves through the crash untouched, splitting from the gas we can see. This made 2 different gravity bending spots, as seen. Along with dark matter, space scientists use Type Ia supernovae as standard candles to measure how far things are across the universe. These supernovae have a known brightness, so by checking how dim they look, scientists can find out how far away they are. This method has shown that the universe is growing faster and faster, something usually explained by dark energy. Baryon acoustic oscillations, BAO, mean regular changes in the thickness of normal matter, baryons, in the universe, which happened on large scales in the early universe. These changes were caused by sound waves moving through the hot, thick mix of light particles and baryons before the universe cooled enough for atoms to form. The effects of these sound waves can still be seen in the cosmic microwave background light. As the universe grew, dark matter and normal matter began to stick together, but the effect of the first changes got weaker over time. However, we can still see a small pattern where galaxies are more likely to be spaced about 147 million light-years apart, which is a small but measurable sign of these early changes. This pattern was guessed in the 1990s and proven in the year 2005 through large galaxy surveys like the Sloan Digital Sky Survey and the 2-degree field galaxy redshift survey. By putting together cosmic microwave background results with BAO measurements, scientists can get a clear estimate of important universe numbers, like how fast the universe is growing and how much matter it has. These results support the lambda CDM idea, which is the main theory of how the universe works today. Big surveys of galaxy redshifts help us make a 3-dimensional map of where galaxies are across the universe, but these maps are not perfect because the distances we guess are based on the redshift we see. The redshift we measure is affected by 2 things. The main reason is the universe's growth, but there's also a smaller effect from the galaxy's own motion, called its peculiar speed. In general, superclusters, groups of many galaxies, are growing more slowly than the average growth of the universe because their gravity is pulling things inward. On the other hand, empty areas, huge spaces with very few galaxies, are growing faster than the universe as a whole. This difference in growth causes some interesting effects. For example, galaxies that are in front of a supercluster are moving toward it faster than expected, so their redshift will be a little higher than we would normally expect for their distance. In contrast, galaxies behind the supercluster seem to have a slightly lower redshift than expected. This difference makes superclusters look flattened when we look straight at them, while empty areas look stretched. But this effect is hard to see in one single shape, since we don't know its exact look. Instead, scientists can see this effect by averaging results from many shapes. The effect was first guessed by Nick Kaiser in the year 1987 and was later proven in the year 2001 by the 2-degree field galaxy redshift survey, with results matching what we expect from the lambda CDM idea of the universe. In a similar area of study, the Lyman alpha forest is the group of light-absorbing lines found in the light spectra of faraway galaxies and quasars. These lines are made by neutral hydrogen blocking light at a certain light wave, called the Lyman alpha transition. Looking at the Lyman alpha forest helps space scientists test and improve their universe ideas with results that agree with the WMAP findings. Dark matter is often split into 3 types: cold, warm, and hot. These names don't mean temperature, but instead describe how fast the particles were moving in the early universe. Simply put, they show how far the particles moved around by chance before the universe started growing and slowing them down. This distance is called the free streaming length, FSL. The kind of dark matter depends on how this FSL compares to the size of a protogalaxy, an early space object that would later become a small galaxy. If the FSL is much smaller than the size of a protogalaxy, it's called cold dark matter. If it's about the same size, it's warm dark matter, and if the FSL is much bigger, it's hot dark matter. Some ideas suggest a mix of these types, which were more common in the middle of the 1990s, but became less popular after the finding of dark energy. The main idea behind the free streaming length is that, after the Big Bang, the universe started with small thickness changes, caused by tiny random changes at the smallest levels. As these particles moved from thicker areas to thinner ones, the fast growth of the universe limited how far they could go. Faster particles, like those in hot dark matter, could move further before the universe got too big, while slower particles, like those in cold dark matter, couldn't go very far. This means that the free streaming length sets a limit on how big the shapes in the early universe could get. Hot dark matter would lead to the making of large shapes, like superclusters, which would later break into galaxies. Cold dark matter, however, allows smaller shapes, like galaxies, to form first. Recent observations, especially deep space pictures, show that galaxies formed first, followed by galaxy groups and superclusters as galaxies came together. This supports the idea that most dark matter is cold, not hot. This is also why neutrinos, which move nearly at the speed of light and would be hot dark matter, cannot explain most dark matter. Dark matter means any kind of matter that pulls on regular matter, like stars and planets, mostly through gravity. This means that dark matter might not be a totally new type of particle, but could, in theory, include normal matter like protons or neutrons. In fact, many things space scientists already know, like planets, brown dwarfs, red dwarfs, stars, white dwarfs, neutron stars and black holes, fit into this group. For example, when a black hole pulls in matter, it doesn't tell the difference between normal matter, like protons, and other kinds. Once it's inside the event horizon, all matter is treated the same. These hard-to-see objects are called MACOs, massive compact halo objects. Some scientists once believed that MACOs made up most of dark matter, but this idea has now been mostly rejected. There is strong proof showing that most dark matter is not made of normal visible matter. First, if there were enough normal matter like gas or dust spread around, we would be able to see it when starlight shines on it. But we don't see this kind of matter in the amounts we would expect. The Big Bang theory helps us understand how the elements we observe today were created. According to this theory, if there were more normal matter, called baryons, in the early universe, we would have seen a higher abundance of elements like helium, lithium, and other heavier elements. Based on what we observe, we know that only about 4 to 5% of the universe's total mass consists of this regular matter. However, large-scale studies of galaxies and other cosmic structures show that the total amount of matter is about 30% of what is needed to keep the universe stable. Further investigations have shown that only a small portion of dark matter seems to be in the form of regular hidden objects, like small planets or black holes, called MACHOs. Studies involving the bending of light by gravity, gravitational microlensing, suggest that these objects can't account for the majority of dark matter, as their masses fall within a range that excludes nearly all of the plausible candidates. Detailed studies of the cosmic microwave background, the faint radiation left over from the Big Bang, by missions like WMAP and Planck, provide strong evidence that about 5/6 of the matter in the universe doesn't interact much with light or regular matter, except through gravity. This suggests that dark matter is largely invisible and can only be detected through its gravitational influence. If regular matter, called baryonic matter, doesn't account for most of dark matter, then dark matter must be made of something else, specifically non-baryonic matter. There are two main possibilities for non-baryonic dark matter: new, mysterious particles and ancient black holes from the early universe. Unlike regular matter, these non-regular particles don't help create the elements that formed during the Big Bang, a process known as Big Bang nucleosynthesis. Instead, we only notice them because of the gravitational effects they cause, such as how they bend light, called weak lensing. Some types of dark matter can even interact with each other, self-interacting dark matter, or with normal particles like WIMPs, weakly interacting massive particles. These interactions might produce detectable signs such as gamma rays and neutrinos, which scientists could possibly observe, indirect detection. There are many different candidates for dark matter, each with its own strengths and weaknesses. WIMPs don't have a strict definition, but they are generally thought of as elementary particles that interact through gravity, and possibly other weak forces such as the weak nuclear force. Many theories suggest that WIMPs were created in the early universe, in a similar way to regular particles. These particles would make up what's called cold dark matter. To explain how much dark matter we have today, the WIMP particles would need to be able to destroy each other in a specific way, which matches what would happen if they had masses around 100 billion electron volts and interacted through the electroweak force. This idea is often called the WIMP miracle, because it fits so well with predictions from supersymmetric theories, which extend the standard model of particle physics. A stable partner particle from supersymmetry has long been seen as a prime candidate for dark matter. Researchers are working hard to find WIMPs, by looking for the products of their destruction, such as gamma rays, neutrinos and cosmic rays coming from nearby galaxies. They also use experiments designed to directly detect WIMPs in laboratories, by measuring their interactions with atomic nuclei, or by trying to create WIMPs in particle colliders, like the Large Hadron Collider, LHC. However, in the early 2010s, experiments didn't find strong evidence for supersymmetry, and the LHC results cast doubt on the simplest WIMP ideas. Axions, another candidate for dark matter, are theoretical particles that were first proposed in 1978 by Frank Wilczek and Steven Weinberg. These particles were originally suggested to solve a problem in the theory of quantum chromodynamics, which explains how quarks and gluons interact. Axions are incredibly light and weakly interact with other particles, making them a perfect candidate for dark matter. They could be produced in the early universe and would remain present today, their abundance depending on their mass. Axions are thought to be so light that they could help explain some of the small-scale issues in the lambda CDM model, the leading cosmological model. The axion theory has gained traction in recent years, especially after WIMPs were not detected. The axion's extremely low mass means that quantum effects could potentially explain the small-scale mysteries of dark matter. Primordial black holes, another interesting idea, are thought to have formed in the very early universe, right after the Big Bang. During the period of rapid expansion known as inflation, incredibly dense regions of subatomic matter could have collapsed under their own gravity, creating black holes without the need for a star's death, as is the case with regular black holes. These black holes would predate the formation of the first stars and could have masses ranging from tiny, even as small as atoms, to incredibly large, far beyond typical stellar black holes. The concept of primordial black holes was first suggested in 1967 by Yakov Zeldovich and Igor Novikov, and later by Stephen Hawking in 1971. The idea quickly gained traction as a possible explanation for dark matter. One of the advantages of primordial black holes as dark matter candidates is that the theory behind black holes is already well established in physics, general relativity, and black holes themselves are already known to exist. However, creating primordial black holes might require complex conditions, such as exotic cosmic inflation, or theories beyond the standard model of particle physics. In 2015, gravitational wave measurements from the detection of black hole mergers sparked renewed interest in primordial black holes as dark matter. Some black holes detected by these experiments had masses that seemed too large to be formed by the usual processes, like the collapse of a star. This suggested they could be primordial. However, a study that looked for signs of gravitational lensing from intermediate mass black holes, expected to be dark matter, found no evidence for them, although some researchers suggest this could be due to assumptions about the mass of these black holes. Further observations, like those made by the James Webb Space Telescope, may provide more clarity on this theory. Scientists once thought that incredibly small black holes, known as primordial black holes, might make up a significant portion of dark matter. However, the Voyager 1 spacecraft, which explored beyond the Sun's influence, measured the flow of positrons and electrons and found something surprising. The amount of particles detected was too low, and their energy levels were not what scientists expected. This led researchers to conclude that these tiny black holes are too rare to account for dark matter. Despite this, the idea of dense forms of dark matter continues to be researched, with new theories even suggesting ways to cool dark matter. As of 2018, the mystery remains unsolved. In 2019, further observations of the Andromeda Galaxy showed no signs of microlensing effects, which would be expected if tiny black holes were present, adding more doubt to their existence. However, there's still a gap in our understanding. There is a range of mass smaller than what we can currently detect with optical microlensing, where primordial black holes could potentially make up all of the dark matter. This area remains open for exploration and continues to challenge our understanding of the universe. If dark matter is made of particles that barely interact with anything, an important question arises. Could these particles form objects like planets, stars, or black holes? Historically, the answer has been no, and there are two key reasons for this. It can't easily lose energy. Regular matter forms dense objects like stars and planets, because it can lose energy in many ways. For example, when particles fall inward due to gravity, they can lose energy, which allows them to slow down and condense into more stable objects. Dark matter, however, doesn't seem to have the ability to lose energy because it doesn't interact with other matter strongly except through gravity. Without ways to release energy, dark matter particles that start to get pulled inward would just heat up, speed up, and eventually escape, preventing the formation of compact objects. It doesn't interact in diverse ways. Regular matter interacts through multiple forces, such as gravity, electromagnetism, and the strong nuclear force, allowing it to form complex structures like atoms, stars, and galaxies. For instance, inside stars, particles interact through nuclear fusion, emitting light and neutrinos. In dark matter, we don't see evidence for such interactions beyond gravity, and possibly some weak interactions, but this is still speculation. Without these varied interactions, dark matter doesn't have the ability to form the kinds of structures that regular matter does. If dark matter is composed of subatomic particles, these particles pass through every square centimetre of Earth millions or even billions of times every second. Many experiments are trying to test this idea. While WIMPs, weakly interacting massive particles, have been the most commonly searched for candidates, axions are also getting attention, especially with projects like the Axion Dark Matter Experiment, ADMX. Other possibilities include heavy particles from a hidden sector that only interact with regular matter through gravity. There are two main types of experiments investigating dark matter: direct detection experiments. These look for signs that dark matter particles are scattering off atomic nuclei in a detector. The goal is to measure tiny energy shifts, a few thousand electron volts, caused by these interactions. When dark matter hits an atom, the atom might release energy in the form of light or vibrations which can be detected. To do this well, these experiments need to be as isolated as possible from background interference, which is why they are often conducted deep underground, where cosmic rays don't interfere. Notable underground labs include Stawell Mine, Sudan Mine, and the Gran Sasso National Laboratory. These experiments often use two technologies: cryogenic detectors that measure heat from particle collisions in materials like germanium, noble liquid detectors that detect light produced when a particle hits liquids like xenon or argon. Some well-known experiments in these areas include CDMS, CRIEST, xenon, and LUX. These detectors are especially good at telling dark matter apart from background particles, which mostly scatter off electrons, while dark matter particles scatter off atomic nuclei. Indirect detection experiments. These search for the effects of dark matter particles destroying each other or breaking down. There's currently no confirmed detection of dark matter in direct detection experiments, but these efforts have helped narrow down the possible properties of dark matter particles. One interesting claim comes from the DAMA, NAI and DAMA Libra collaborations, which have noticed a yearly change in their data, possibly due to the Earth's movement through the dark matter cloud. However, other experiments such as LUX and super CDMs have not seen the same effect, creating a bit of a mystery. There are also special experiments with directional sensitivity, which track the motion of dark matter particles based on the solar system's movement around the galactic center. This method tries to separate dark matter signals from background noise, which should be evenly spread out. These experiments, such as DMTPC and DRIFT, try to detect the direction in which dark matter is moving to help find possible signals. Indirect detection experiments aim to find signs of dark matter by looking for the results when dark matter particles self-destruct or break down in space. In certain areas with high amounts of dark matter, like the center of the Milky Way, two dark matter particles might collide and destroy each other, releasing gamma rays or pairs of normal particles and their opposites, antiparticles. Alternatively, if a dark matter particle is unstable, it might break down into normal particles or others, which could be detected indirectly through an unexpected burst of gamma rays, antiprotons or positrons coming from areas with a lot of dark matter, like the Milky Way's center or distant galaxies. One of the challenges of this kind of search is that other space events could produce similar signals, so multiple signals from different sources are needed to confirm a dark matter discovery. Dark matter particles that pass through the Sun or Earth might interact with atoms and lose energy in the process. This could cause dark matter to build up at the centers of these celestial bodies, increasing the chances for collisions or destruction. These events could send out a special signal of high-energy neutrinos, which could serve as strong evidence of dark matter made of WIMPs, weakly interacting massive particles. Instruments like Amanda, IceCube, and Antares are actively searching for this signal. In addition, the detection of gravitational waves by LIGO in 2015 opened the door for observing dark matter in new ways, especially if it exists as early black holes. Several experiments have tried to detect dark matter emissions, such as those from destruction or breakdown. For example, the Energetic Gamma Ray Experiment Telescope spotted more gamma rays in 2008 than expected from the Milky Way, but scientists believe this was due to errors in estimating the telescope's sensitivity. The Fermi Gamma Ray Space Telescope is continuing this search, and, in 2009, it observed a puzzling extra amount of gamma rays from the centre of the Milky Way. This could be a sign of dark matter destruction or an unknown group of pulsars. In 2012, a deeper analysis of Fermi data suggested a 130 giga-electron-volt signal from the Milky Way's centre, which was interpreted as a possible result of WIMP destruction. At even higher energies, ground-based telescopes have set limits on dark matter destruction in dwarf galaxies and galaxy groups. The Pamela experiment, launched in 2006, detected an unusual amount of positrons, which might come from dark matter or pulsars, though no similar excess of antiprotons was found. Similarly, the Alpha Magnetic Spectrometer aboard the International Space Station observed high-energy cosmic rays in 2013, possibly linked to dark matter destruction. Another approach to finding dark matter involves trying to create it in a laboratory. Experiments like those at the Large Hadron Collider, LHC, may detect dark matter particles formed during proton collisions. Since dark matter doesn't interact much with regular matter, it might be spotted indirectly by noticing large amounts of missing energy and momentum that escape detection, while other particles from the collision are measured. The LAP experiment, using a similar method but probing the interaction between dark matter and electrons, also provides limits on dark matter. Any discovery of dark matter in such experiments must be verified by findings from indirect or direct detection methods to confirm that the new particle is truly dark matter. Because scientists still haven't figured out exactly what dark matter is, many other ideas have been suggested to explain the strange things we see happening in the universe. One of the biggest clues pointing to dark matter comes from a theory called general relativity, which explains how gravity works. This theory has been tested many times and works very well when used to understand things within our solar system. But when scientists try to apply it to entire galaxies or the whole universe, it hasn't been fully proven to work the same way. Some researchers believe that maybe the problem isn't with missing matter, but with the theory of gravity itself. In other words, instead of searching for something invisible like dark matter, maybe we just need to change the rules of gravity to match what we observe. Over the years, a number of different ideas have been put forward as alternatives to dark matter. Some of the most talked about ones include MOND, which stands for Modified Newtonian Dynamics, TeVS, which is a more detailed version of MOND, a theory called FR gravity, the idea of negative mass, something known as dark fluid, and another concept called entropic gravity. The big problem with all these alternative theories is that the clues we have for dark matter come from many different places. For example, we see its effects in how galaxies move, how light bends around massive objects, how the universe has grown over time, and more. An alternative theory might be able to explain one or two of these observations, but it is extremely hard to explain all of them without dark matter. Still, some of these new ideas have shown small signs of promise. For example, in the year 2016, scientists carried out a test related to gravitational lensing, the bending of light by gravity, that gave some support to the idea of entropic gravity. And in the year 2020, another study found results that seemed to agree with the predictions made by MOND. Even though these are interesting results, most scientists who study space still think that the best explanation is that dark matter does exist, even if we don't know exactly what it is yet. While it's possible that tweaking the rules of gravity could help explain some things, the large amount of evidence we have overall points toward dark matter being real in some form. The universe is growing bigger over time, a discovery first made nearly 100 years ago. In the late 1920s, the astronomer Edwin Hubble noticed that distant galaxies were moving away from us, meaning the universe was expanding. This was a huge revelation, and it changed the way scientists thought about the cosmos forever. For many decades after Hubble's discovery, most scientists believed that, although the universe was expanding, the pull of gravity from all the matter in it, stars, planets, gas, dust, and dark matter, would slowly slow it down. They imagined it like throwing a ball into the sky. At first, it goes up quickly, but gravity eventually slows it and brings it back down. In the same way, they thought the universe's expansion would lose speed over time and maybe even stop or reverse someday. But everything changed in the late 1990s. Two separate teams of scientists were studying very distant exploding stars called Type Ia supernovae. These explosions are extremely bright and always happen when a certain kind of star, a white dwarf, gathers too much material from a nearby companion and crosses a limit known as the Chandrasekhar limit. Because they always explode in the same way, with the same brightness, astronomers use them as standard candles. That means they can figure out how far away they are based on how dim they appear to us. When the scientists looked at these supernovae, they found something shocking. The distant supernovae were dimmer than expected. That meant they were farther away than they should have been if the universe was slowing down. This surprising result showed that the expansion of the universe wasn't slowing down, it was actually speeding up. This unexpected discovery revealed the presence of a mysterious force that was pushing galaxies apart faster and faster. Scientists gave this strange force a name, dark energy. Today, dark energy is believed to make up about 68% of all the energy and matter in the universe, making it the largest and most powerful part of our entire cosmos. Its influence stretches across time, shaping the past, present, and future of the universe. Interestingly, the idea of something like dark energy had already appeared in science nearly a century earlier. In the year 1917, Albert Einstein added a special term to his new theory of general relativity. He called it the cosmological constant, and he used it to keep the universe static, because back then, scientists believed the universe wasn't expanding or shrinking. But when Hubble later showed that the universe was indeed expanding, Einstein called the constant his biggest blunder. For many years, the cosmological constant was forgotten, but it never completely went away. When scientists found out that the expansion of the universe was speeding up, the idea of the cosmological constant came back into the spotlight. Now, it seemed, Einstein's blunder might actually explain something deeply important about the universe. The two teams who made the discovery of the accelerating universe were the Supernova Cosmology Project, led by Saul Perlmutter, and the High Z Supernova Search Team, led by Brian Schmidt and Adam Rees. Both groups worked independently, but they reached the same conclusion. Their findings were so important that in the year 2011, Perlmutter, Schmidt and Rees were awarded the Nobel Prize in Physics. But supernovae weren't the only clue pointing to dark energy. Another powerful piece of evidence comes from a faint glow left over from the early universe called the Cosmic Microwave Background, or CMB. This radiation is a snapshot of the universe when it was just about 380,000 years old. By studying tiny changes in the temperature of the CMB, especially certain patterns known as acoustic peaks, scientists can learn about the shape of the universe and the amounts of different types of matter and energy in it. Data from space missions like WMAP and Planck showed that the universe is flat, which means parallel lines never meet or spread apart even across the vast stretches of space. For the universe to be flat, it must have a very specific total energy density. But when scientists added up all the visible matter and the invisible dark matter, they only got about 32% of the amount needed. The missing 68% had to come from something else, and that something else was dark energy. More evidence comes from how galaxies and large structures are spread across the universe. Normally, gravity pulls matter together to form stars, galaxies, and clusters. But dark energy pushes space apart, slowing down this gathering process. By studying the number of galaxies and how they are grouped at different points in time, scientists can see the effect of dark energy. One especially important clue comes from something called baryon acoustic oscillations, or BAOs. These are like frozen sound waves from the early universe that left a distinct pattern in how galaxies are spread out. Scientists use this pattern as a kind of standard ruler to measure the universe's expansion. These measurements also confirm that the universe is expanding faster and faster, just like the supernova and CMB data show. So, what exactly is dark energy doing? According to general relativity, gravity isn't caused just by mass, it's also affected by pressure. While normal substances like gas have positive pressure that pulls things together, dark energy has negative pressure. This unusual pressure does the opposite, it pushes space apart. One possible explanation is that empty space itself has energy, called vacuum energy. As space grows, more vacuum energy appears, keeping the energy density constant but increasing the total amount. This leads to more and more pushing, speeding up the universe's expansion. The simplest theory for dark energy is still Einstein's cosmological constant, just the energy of empty space. But quantum physics predicts that this vacuum energy should be much, much larger, up to a trillion times greater than what we actually observe. This massive difference is called the vacuum catastrophe, or the cosmological constant problem, and it's one of the biggest mysteries in science. Other ideas suggest that dark energy might not be constant at all. It could be something that changes over time, like a field that spreads across the universe and slowly evolves. This kind of theory is called quintessence. It works a bit like the Higgs field, which gives particles their mass. If quintessence exists, it might explain why dark energy became important only in recent cosmic history. But proving this idea is hard, and scientists haven't yet found solid evidence for it. Another group of theories suggests that maybe we don't need dark energy at all. Maybe gravity itself changes over large distances. These modified gravity theories propose that the laws of gravity we know from Einstein's equations work perfectly at small scales, like around stars and planets, but act differently over the huge distances between galaxies. These models are fascinating, but they must match every observation we've made so far, which makes them difficult to get right. What does all this mean for the future of the universe? If dark energy keeps acting like a cosmological constant, then the universe will continue to expand faster and faster forever. This future is called the Big Freeze or heat death. In this scenario, galaxies far away from us will disappear beyond our reach, pulled away faster than light can travel. Eventually, even nearby galaxies might get pulled apart. Stars will burn out, black holes will slowly vanish, and the universe will become a cold, dark, and empty place with nothing but slowly fading radiation. But there are other, more extreme possibilities. If dark energy becomes even stronger over time, it could lead to a catastrophic end called the Big Rip. In this scenario, the force of expansion would grow so powerful that it would tear galaxies, stars, planets, and even atoms apart. On the other hand, if dark energy weakens or reverses, gravity might take over again. The universe could stop expanding and begin to shrink, ending in a big crunch, a collapse back into a single point, the opposite of the Big Bang. Right now, all the evidence points to the cosmological constant being the best explanation. That means the Big Freeze is the most likely fate awaiting our universe. The idea of dark energy brings up a strange and puzzling question known as the cosmic coincidence problem. This mystery asks, why is it that right now, in the present age of the universe, dark energy has become just as important as matter in terms of its effect on the universe's expansion? Why not earlier or later? This is especially strange because dark energy has only become stronger than matter recently, on cosmic timescales. Billions of years ago, the universe was filled mostly with matter, and gravity caused this matter to clump together, forming stars, galaxies, and clusters of galaxies. If dark energy had been stronger than matter much earlier, the universe would have expanded too quickly for galaxies to form at all. On the other hand, if dark energy had shown up much later, the universe would have remained dominated by matter for a very long time, and we might not be here now to ask these questions. So, why is dark energy becoming important right now, just at the time when intelligent life like us has appeared and is able to observe it? Is this just a strange coincidence? Or is there some deeper connection between the conditions of the universe and the appearance of life? Some scientists think this could be explained by something called the anthropic principle, which suggests that the universe has the properties it does because only certain types of universes can support life, and we naturally find ourselves in one of those. Others take this idea further and suggest the multiverse, the idea that there may be many different universes, each with different properties. In this view, we just happen to live in one where dark energy appeared at just the right time to allow galaxies, and eventually life, to form. This puzzle is still one of the most fascinating open questions in science today. The search to understand dark energy is one of the biggest and most exciting challenges in modern cosmology. Scientists all around the world are working hard to study it more closely. Over the coming years, several powerful space and ground-based telescopes will help us learn more. These include the Nancy Grace Roman Space Telescope, the Euclid Mission, and the Vera C. Rubin Observatory. These observatories are being specially designed to collect precise data about how the universe has grown and changed over time. By carefully observing how galaxies are spread out across space, and by studying the brightness of distant exploding stars called supernovae, scientists hope to find out whether dark energy is truly a constant force, something that never changes, or if it might evolve over time. If dark energy does change, it could mean that we're dealing with something very different from what Einstein originally called the cosmological constant. It might instead be something called quintessence, a kind of energy that slowly changes as the universe expands. These future discoveries could also help rule out some theories that try to change or replace Einstein's theory of gravity altogether. Figuring out what dark energy really is could completely change how we understand the universe. It could teach us new things about gravity, about how tiny particles behave, and even about the ultimate fate of everything that exists. Will the universe expand forever? Will it slow down? Or will something completely unexpected happen? Before the dawn of the 20th century, most scientists believed that space and time were completely separate things. Space was imagined as a giant three-dimensional stage, a sort of invisible box, where all the stars, planets, and people existed and moved around. Time, on the other hand, was thought to flow like a steady river, ticking by the same way for everyone, everywhere, no matter what. This simple and intuitive idea matched our everyday experiences and had worked well for centuries. This way of thinking formed the foundation of Newtonian physics, named after Sir Isaac Newton. His ideas successfully explained how things moved and how gravity worked, from falling apples to the paths of planets in the sky. For hundreds of years, Newton's laws were considered the ultimate truth when it came to motion and gravity. But everything changed in the early 20th century, thanks to the brilliant and imaginative mind of Albert Einstein. His revolutionary theories, special relativity and later general relativity, completely transformed the way we understand space, time, and gravity. Einstein showed that space and time are not separate at all. Instead, they are deeply connected and form a single, four-dimensional fabric called spacetime. This astonishing concept became the key to answering some of the most profound questions about the universe and the nature of reality itself. Einstein's journey began in the year 1905, when he published a paper introducing the special theory of relativity. This theory focuses on how space and time behave when objects are moving at steady speeds, especially very fast speeds, in the absence of gravity. At its heart are two simple but powerful ideas called postulates that Einstein treated as fundamental truths based on experiments and logic. The first postulate is called the principle of relativity. It says that the laws of physics, whether you're talking about electricity, magnetism, or mechanics, are exactly the same for everyone who is moving at a constant speed in a straight line. Imagine you're in a windowless room on a train moving at a steady pace. No matter what kind of experiment you perform, you wouldn't be able to tell whether the train is moving or standing still. Everything would work exactly the same. This idea wasn't entirely new. Long before Einstein, Galileo Galilei, in the 17th century, had noticed something similar when talking about ships and motion. But Einstein extended this idea to include all the laws of physics, not just mechanical ones. The second postulate is even more surprising. It says that the speed of light in a vacuum is always the same, no matter how fast you're moving or how fast the light source is moving. Light always travels at about 300,000 kilometers per second, or roughly 1,080,000,000 kilometers per hour. This was a shocking idea at the time because it broke the rules of classical physics, where speeds were simply added or subtracted. For example, if you throw a ball forward on a moving train, the ball's speed is the speed of your throw plus the speed of the train. But with light, this rule doesn't apply. Whether you're running toward a beam of light or away from it, you will still measure its speed to be exactly the same. These two postulates have mind-bending consequences. One of the most famous is something called time dilation. This means that time actually runs slower for objects moving at high speeds compared to objects that are at rest. Imagine two identical clocks. One stays on Earth, while the other is placed on a spaceship travelling at a speed close to the speed of light. When the spaceship returns, the clock on board will show less time has passed than the clock on Earth. In other words, time moved more slowly for the fast-moving spaceship. This is not just a theory. It has been proven in real-life experiments. For example, atomic clocks flown on airplanes have shown slight differences in time compared to clocks left on the ground. Another example comes from muons, tiny particles created high in the Earth's atmosphere. Muons normally live for only a tiny fraction of a second, but when they move at speeds close to the speed of light, they appear to live longer from our point of view, long enough to reach the Earth's surface. This shows that time is not absolute. It depends on how fast you're moving. Another strange effect is called length contraction. If an object moves very fast relative to an observer, its length appears to shrink in the direction it is moving. For example, a spaceship flying past Earth at near light speed will look shorter to someone on Earth than it would if it were standing still. But from the point of view of someone on the spaceship, it is the Earth that appears to be shortened. Again, this is a real effect, not an illusion, though it's only noticeable at extremely high speeds. Special relativity also leads to the idea of relative simultaneity. This means that two events that happen at the same time for one person might happen at different times for someone else who is moving relative to them. There is no universal now that is the same for everyone. What one person considers to be the past might still be in the future for someone else. This deeply challenges our common sense ideas about time and the flow of events. Einstein's discoveries made it clear that space and time were deeply connected. This led Hermann Minkowski, a former teacher of Einstein, to come up with a new idea, the concept of space-time. He realized that if time and space change depending on how you move, then they must be part of one four-dimensional structure. Minkowski famously said, "Space by itself and time by itself are doomed to fade away into mere shadows. Only a kind of union of the two will preserve an independent reality." In this new picture, events are like dots in space-time, and the paths objects follow through space-time are called world lines. Special relativity had revealed this new way of thinking, but it still didn't explain how gravity fit into the picture. That challenge would lead Einstein to his next major breakthrough. Einstein spent the next 10 years searching for a way to include gravity in his new theory of the universe. Newton's idea of gravity, which described it as an invisible force acting instantly across space, didn't fit with the idea that nothing can travel faster than light. Einstein's breakthrough came in the year 1915 with his general theory of relativity. This theory said something amazing. Gravity isn't really a force at all. Instead, it's the result of the bending or warping of space-time by mass and energy. The core idea behind general relativity is called the equivalence principle. It says that you can't tell the difference between the effects of gravity and the effects of acceleration. For example, if you're inside a sealed elevator in deep space and it suddenly starts moving upward, you would feel pressed to the floor, just as if you were standing in gravity. And if the elevator were falling freely, you'd feel weightless, just like astronauts in orbit. This led Einstein to realize that gravity is not a mysterious pulling force, but rather the natural result of objects moving through curved space-time. To understand this, picture a stretched rubber sheet. If you place a heavy ball in the middle, it creates a dip. Now roll a smaller ball nearby. It will move in a curved path, not because the heavy ball is pulling on it, but because the sheet itself is bent. This is how planets orbit the Sun. The Sun's huge mass creates a deep dip in space-time, and the planets follow the curved paths around it. The greater the mass of an object, the more it bends space-time around it. And just like marbles rolling across a curved sheet, other objects move along these curves. Gravity, then, is really just the result of moving through this warped fabric of space-time. Einstein's ideas forever changed how we see the universe. His theories of relativity didn't just replace Newton's, they gave us a deeper understanding of reality, showing us that space and time are not fixed and absolute, but flexible and interwoven. They laid the foundation for modern cosmology, helping us explore everything from black holes to the Big Bang, and even the strange mysteries of time itself. Albert Einstein's theory of general relativity made some truly amazing predictions, ideas that sounded almost unbelievable at first, but were later proven to be true through careful observation and experimentation. One of the first and most famous of these predictions was the idea that gravity could actually bend light. Einstein explained that space and time are not separate things, but are woven together into what he called space-time. Massive objects like the Sun don't just sit in space-time, they actually bend and curve it. And when light passes near such a massive object, it doesn't follow a straight path. Instead, it curves slightly, just like a marble rolling across a dented trampoline. This bold idea was tested in the year 1919 during a total solar eclipse. A British astronomer named Arthur Eddington led an expedition to observe stars that appeared near the Sun while it was blocked out by the Moon. When they looked at the stars whose light had passed close to the Sun, they saw something remarkable. The stars appeared to be slightly out of place, just as Einstein had predicted. Their light had been bent by the Sun's gravity. This dramatic confirmation made Einstein world famous overnight and gave a huge boost to the acceptance of general relativity. Another strange but important prediction from Einstein's theory is something called gravitational redshift. This refers to the way light changes color when it moves through gravity. When light travels upward, away from a strong gravitational source, like a star, it loses a bit of its energy. As a result, its waves stretch out, making it appear more red. On the other hand, if light moves downward, deeper into gravity, it gains energy and shifts toward the blue part of the spectrum. Scientists have tested this in laboratories using ultra-precise atomic clocks. They have also seen it happen in space, for instance, when light escapes from very dense stars called white dwarfs. The escaping light appears slightly redder because it's been stretched out by gravity. But perhaps the most dramatic and exciting test of general relativity happened only recently. Back in the year 2015, scientists made the first direct detection of gravitational waves, tiny ripples in the very fabric of space-time. Einstein had predicted the existence of these waves 100 years earlier, saying they could be caused by massive cosmic events, like two black holes smashing into each other. But these waves are incredibly faint, and it took many decades and the development of extremely sensitive technology to finally find them. The discovery came thanks to a project called LIGO, short for Laser Interferometer Gravitational Wave Observatory. In that historic moment in 2015, LIGO detected waves coming from a collision between two black holes that happened over 1 billion years ago. It was a breakthrough that didn't just confirm Einstein's theory once again, it opened a completely new way to observe the universe, allowing us to hear cosmic events that don't produce any light at all. Einstein's theory also explained something that had puzzled astronomers for a long time: the way the planet Mercury moves around the Sun. Newton's laws couldn't fully account for a tiny twist in Mercury's orbit, but general relativity did. Another amazing prediction of Einstein's theory is the existence of black holes, places in space where gravity is so strong that nothing, not even light, can escape. In these regions, matter is crushed into a point so dense that space-time itself is pushed to its limits. The study of black holes continues to be one of the most exciting areas in science, constantly testing how far general relativity can go. One of the most mind-bending ideas to come from general relativity is the way it changes our understanding of time itself. In the old view of the universe, as imagined by Isaac Newton, time was like a never-ending river flowing steadily in one direction, completely separate from space. But Einstein showed that time is not separate at all. It is connected to space, and the two together form the fabric of space-time. Time can actually speed up or slow down depending on how fast you're moving or how strong gravity is where you are. In other words, time is not absolute. This leads to a truly astonishing idea. If space-time had a beginning, then time itself had a beginning. According to the Big Bang model, the best current explanation for how the universe started, space, time, matter, and energy all came into existence together. There was no before the Big Bang, because time itself did not exist yet. Asking what happened before the Big Bang is like asking what's north of the North Pole. The question doesn't really make sense because you're asking about something beyond the limits of the system. This idea changes the way we think about beginnings altogether. The moment of the Big Bang wasn't an explosion in space. it was the creation of space and time itself. This means that the origin of the universe is also the origin of time. It's a concept that challenges our common sense, but it lies at the heart of modern cosmology. So the idea of space-time, a single, unified fabric that combines both space and time, is not just a fancy theory written down in equations. It's a real, physical thing that scientists have been testing for over 100 years. Its bending is what we feel is gravity. It's the stage on which every event in the universe plays out. Understanding this fabric helps us look back into the deep past, understand the present, and even make guesses about the future of the universe. And perhaps most importantly, it prepares us to face the biggest and strangest questions of all. How did everything begin? What does it mean for time to start? And could something lie beyond the horizon of time as we know it? These are the mysteries that general relativity leads us toward, and they continue to inspire scientists, thinkers, and dreamers around the world. In our everyday world, things seem to behave in very logical and predictable ways. A ball thrown into the air follows a clear path. A car moves only if someone presses the gas pedal. One thing leads to another in a chain of causes and effects. Objects have clear positions and move with clear speeds. This simple and intuitive understanding of how the world works was deeply rooted in the ideas of Isaac Newton, whose laws of motion and gravity were the gold standard of science for more than 300 years. But as the 20th century began, scientists started to look deeper into the universe, peering into the tiniest building blocks of nature, atoms and the particles within them. What they found was shocking. The rules that govern the very small, the world of particles and waves, were nothing like the ones we know from our daily lives. It was as if nature had a completely different rulebook for its tiniest components. This new rulebook became known as quantum mechanics, and it would forever change how we think about reality. Quantum mechanics didn't just update a few details. It forced scientists to rethink what it even means for something to exist. And these strange quantum ideas are not just theoretical. They are essential for understanding the universe in its earliest moments, right after the Big Bang, and they form the heart of an exciting field called quantum cosmology. Quantum mechanics was born out of confusion about things that classical physics simply couldn't explain. One of the first big puzzles was something called blackbody radiation, how objects glow when heated. According to classical theories at the time, a hot object should release an infinite amount of ultraviolet light. This prediction was nonsense, and the problem became known as the ultraviolet catastrophe because it clashed with everything scientists actually observed. Then, in the year 1900, a German physicist named Max Planck came up with a radical solution. He suggested that energy isn't given off smoothly and continuously. Instead, it comes in small chunks or bundles, which he called quanta. The amount of energy in each quantum depended on the frequency of the light, and the link between energy and frequency became known as Planck's constant, a number that still plays a key role in quantum physics today. Although Planck didn't realize it at the time, this idea was the beginning of a revolution in science. He thought he was just using a clever trick to fix the equations, but he had actually opened the door to an entirely new understanding of nature. Another mystery involved something called the photoelectric effect. Scientists had noticed that when light shines on a metal surface, it can knock out electrons. Classical wave theory said that the more intense the light, the more energy the electrons should have, no matter the color or frequency of the light. But experiments showed something completely different. If the light's frequency was below a certain limit, nothing happened, no matter how bright the light was. But if the frequency was high enough, even dim light could knock out electrons. The energy of the ejected electrons depended not on the brightness, but on the frequency of the light. In the year 1905, Albert Einstein offered a bold explanation. He proposed that light itself is made of individual particles or photons, and each photon carries a specific amount of energy based on its frequency. An electron could only be knocked out if it absorbed one photon with enough energy to break free. If the photon's energy wasn't high enough, no electron would budge, no matter how many photons you sent. This idea, that light acts like both a wave and a particle, was another step into the strange world of quantum mechanics. Perhaps the most famous and strangest feature of quantum mechanics is something called wave-particle duality. In the everyday world, Something is either a wave or a particle. A baseball is a particle. A ripple in a pond is a wave. But in the quantum world, particles like electrons and even light can behave as both. This is beautifully shown in the famous double-slit experiment. Imagine you have a screen with two narrow openings and you shoot tiny electrons at it one at a time. You'd expect them to pass through one slit or the other, like little bullets, and make two bands on a screen behind it. But that's not what happens. Instead, the electrons create an interference pattern, a series of bright and dark bands, as if each electron was acting like a wave and somehow went through both slits at once, interfering with itself. It's as if the electron was spread out like a wave during its journey. But here's the strange part. If you set up a detector to watch which slit the electron goes through, the interference pattern disappears. Now the electrons act like little particles again, choosing just one slit. The very act of observing the electron changes its behavior. This bizarre result reveals a deep truth. At the quantum level, observation affects reality. Another key idea in quantum mechanics is superposition. This means that a particle like an electron doesn't exist in just one state, like being here or there. Instead, it exists in many possible states at once, like a cloud of possibilities. Only when we measure or observe the particle does it collapse into one specific state. To help imagine this, the Austrian physicist Erwin Schrödinger came up with a famous thought experiment in the 1930s. Picture a sealed box with a cat inside. There's a vial of poison that will break open if a single radioactive atom decays, but until someone opens the box, quantum mechanics says the atom is both decayed and not decayed at the same time. This means the cat is both alive and dead. A bizarre superposition of two realities. Only when the box is opened does the cat become clearly alive or dead. Of course, this is not meant to describe real cats. It's a way to highlight how strange the quantum world truly is. In classical physics, if you know everything about a system, its position, speed, and other properties, you can predict exactly what it will do next. But quantum mechanics doesn't work that way. Instead of giving exact predictions, it gives probabilities. You can only calculate the likelihood of finding a particle in a certain place or in a certain state. The equations of quantum mechanics use something called a wave function, which contains all the possible outcomes. The Born rule tells us that the square of the wave function's amplitude gives the probability of finding the particle at a particular location. This randomness is not due to poor instruments or a lack of knowledge. It is built into the fabric of the universe itself. This strange idea was made even clearer by Werner Heisenberg in the year 1927, when he introduced the uncertainty principle. He showed that you can never know both the exact position and the exact momentum of a particle at the same time. The more accurately you know one, the less you can know the other. There's a similar uncertainty between energy and time. The better you know the energy of a system, the less precisely you know how long it had that energy. This is not just a limitation of our tools, it is a fundamental feature of reality. One of the biggest puzzles in quantum mechanics is the measurement problem. When a particle is in superposition, existing in multiple states at once, what exactly causes it to collapse into a single outcome when we observe it? Some physicists believe it's the interaction with a measuring device. Others think consciousness might play a role. Different interpretations of quantum mechanics, like the Copenhagen interpretation or the many worlds interpretation, try to explain this, but no single view has been universally accepted. Another fascinating quantum phenomenon is entanglement. When two particles become entangled, their states become linked, even if they are far apart. Measuring one particle instantly affects the other, no matter the distance between them. This seems to violate the rule that nothing can travel faster than light, but it doesn't actually allow us to send messages that fast. Still, it shows how deeply connected the universe is at the quantum level. Modern physics takes things even further with quantum field theory. This theory says that every particle is actually a small ripple in a field that fills all of space. For example, there is an electron field, a photon field, and so on. Particles are just the visible tip of these vibrating fields. Even the vacuum of space isn't empty. It's full of potential energy and virtual particles that can pop into and out of existence. This strange energy helps explain some of the mysteries of the universe. At the very beginning of time, during the Big Bang, classical physics breaks down. Einstein's general relativity predicts a singularity, a point of infinite density and temperature. But to understand what really happened in the first moments, about 10 to the power of minus 43 seconds after the beginning, we need a new theory that combines quantum mechanics with gravity. This unknown theory is called quantum gravity, and it holds the key to the universe's true origin.